the development of this IT era throughout the world. Though India has missed the Industrial Revolutions 1, as well as World War and World War II, for participating in the industrialization of the whole country, as well as some development of advanced technologies. But IT era, we have proved our worth and earned a lot for our country, and many of our young generation has got excellent job, not only within the country, outside, and they brought a lot of wealth to our country. The same way the nanomaterials, robotics, automation technology, IoT and all going to happen, because a cluster of small groups with highly intellectual contents can show better progress in this area. And this is a good area and many are pursuing. So we urge the people to pursue their intense research in this area. So this is the initiative taken by my predecessor, Professor Ramachandran, and the physics and chemistry department of the NIT Nagaland, and they are doing good research in this area, particularly nanomaterials, magnetic materials, and electronic materials, which is unique in this area, which is compared to instead of duplicating the research which are going on outside of this country. Now, as a new institute, we have got ample of opportunity to orient our research to the new direction, to the region specific, and the very good dedicated students as well as youngsters are there in the North Eastern region, so they can work calmly, comfortably in these areas, and it is our duty of the institute to provide better facilities. Towards this, we are also doing to the not great extent, to the extent a few PhD theses have rolled out and few patents have been filed in the past, and many of the students have shown interest in pursuing research in these advanced areas. And we are also developing our infrastructures for this. I hope that many students will join and take this to the culmination of very good products and more patents and more products and useful to our society. With this small introduction, I once again welcome all the participants through online. But Nagaland, it is a beautiful place, greeneries, it is Switzerland of India, and the people are warm. And you can, very good scenery, excellent greenery. You saw one thing is the greenery is always pleasant. That you see that one remarkable things when I came here and noticed that because of this greenery, the persons like wearing spectacles are less in this equipment. Other side, you can see all these institutions, those who are in toppers, they will get thick spectacles as our standard. So it is not that much, it is greenery. Even it is changes in the psychological moods of a person. So I extend warm welcome to visit our campus. Though after this pandemic, we will make this series of those, because of that only delayed. Earlier the plan was once in 2 years this conference will be conducted here. Because of the pandemic, we thought that it will be over, we can physically meet. Even last week also we are thinking that we can physically meet, and they made all the arrangements to have. But unfortunately, we could meet through our online mode only away. But anyway, our minds are together. Because olden days when I am residing, when the polarization of mind, one classical example of construction of monuments, temples and all in our country. You see that time there is no drawing, no CAD drawings and things. People will sit and meditate and meditate. After some time, they will start working on that. When they are making a big sculpture or anything, one fellow taught at the top, another person is right foot, another person left foot, like that. But you see, after 1 month, everything seemingly match, and we will make a very beautiful statue as well a beautiful structure for our country. We can see that in that without any drawing, 3D projections, CAD and animation and all they could do because of the polarization of the mind. Though we are apart, our minds are polarized towards this advanced area. That is more important than physically person. That's what we are seeing nowadays. So polarization of the mind more, and it gives always immense pleasure to see you all here. We hope that another conference we will be conducting in the future after this condensed matter physics. So that time, I request all the participants to visit NIT Nagaland, to interact with our students and identify common areas so that all progress together for the welfare of our country. Finally, one more time, I'm extending my warm welcome for this conference. This conference is an excellent, many invited speakers and keynote address by authorities are delivering and debating. And they are that abstracts, if you go through that, the areas are really frontier areas in the science what we are pursuing. Definitely it will culminate into the useful products and patents in future. So that there's no doubt. So it is the participants. I hope that the participant will be rewarded professionally by attending this conference. And once in 2 years it is coming out. So don't gap attending this conference like attending a marriage function and getting it is not solemnization of something. It is starting for the working together. So working to it is not, we are not, conference is not for solemnization or for some solemnizing something or for congregation, but it is for beginning of the working. Already we will work together and meet together, exchange our ideas and do. With this introduction, I once again congratulate our team headed by Professor Bora and Professor Amit for wonderfully organizing this conference here in spite of lot of difficulties and the hindrance from my side because of the constraint on the fund. I won't because of that also there. I am the more stumbling block for this conference, but anyway, they will excuse because of that. But anyway, economy is more important than anything. That's for economy only these advanced technologies we are generating. So I hope that with a lot of constraints imposed by me, the conference organizers and their students, particularly the science club headed by Ms. Rodi, is a very outstanding personality of the students who is leading these many events to past in successfully. So with that, I compliment them for their hard work and their dedicated services for ably organizing. I thank Professor P. Maganta, in spite of his with a lot of difficulties and struggles, and hard pressed with the time, he could accede my request and be the chief guest of this session. And so similarly, Professor Ramachandran also, he has gladly agreed for our invitation and joined with us. Other personality, Professor Sharma, is very keen. We are also very keen in inviting, but unfortunately, this COVID allows us to be away for more than 2,000 kilometers away. But the minds are in that. His mind is always at NIT Nagaland, I hope. So once again I wish all the best to the participants and make use of the conference and dedicate our souls to the welfare of the society and the country. Thank you so much. Jai Hind.
Thank you so much, sir. It was a delight listening to our director. And I think, yes, for all the participants connecting to us online, it would be a fruitful experience. We'll continue this in the coming years. And now I would like to request the convener of ICET NMST 2022, Dr. J.P. Bora, to share his journey from first day of planning for ICET NMST 2017 to the second edition of ICET NMST 2022. So I'd like to request sir to share a few words. Thank you.
Thank you, Sardi. Good morning, everyone. Respected Chief Guest, Professor Mohanta sir, Director NIT Arunachal Pradesh, and respected Guest of Honor, Professor Ramachandran sir, former Director NIT Nagaland, and Professor Eminent Researcher, Professor D.D. Sharma sir, Professor J.B. Barua sir from IIT Guwahati, and Professor Sirugiri sir, and maybe some more professors, eminent person has joined, but I may not able to mention because my screen view is only limited. So sorry for not mentioning all professors and all the delegates who participate in the conference and the colleagues and my dear students. On the behalf of organizing committee, I just want to extend a welcome to all the participants, keynote speaker, plenary speaker, invited speaker, and the presenter to this conference. And before starting the glimpse of the conference, just want to mention about the NIT Nagaland, because all people may not be aware of NIT Nagaland maybe. So the NIT Nagaland, they started in 2010 from the NIT Silchar, then campus is shifted in 2012 here. And we have now 7 different departments, and we have 6 different BTech courses. And apart from these, we have MSc courses, MSc Physics, and 4 MTech courses. In our department, especially the Science and Humanities, among all the departments, it is a combination of all the sciences department, physics, chemistry, mathematics, and humanities, social science, and English. And in our department, we have a MSc Physics course, we just started in 4 years back, and already 2 batches passed out. And apart from this, we had also in the BSMS courses, because of some issues, stopped the courses, and already 3 batches have passed out. And apart from this, we have a very research environment in our department, and we have a lots of scholars, around 30, more than 30 scholars, and already I think 4 or 5 had already awarded PhD, and they are doing very good job in the different part of the country. And the ICTNMST 2000, that international conference on emerging recent trends in emerging trend in nanomaterial science and technology concept started with the former director, that Professor Ramachandran sir, in 2016. He was the person who initiated this conference. I just want to first thanks to Professor Ramachandran sir for initiating this type of conference. Thank you, sir. And in 2017, we have a witness of more than 120 participants. They included the keynote, plenary, invited talks all around the globe. So the second chapter of ICTMST, now this is the second one, because we are supposed to, the conference will be held on 2 years in a year because of the many constraints, and after that there's a pandemic scenario, we could not able to do the conference before that. So now this conference is held on after 3 years. It is supposed to be 2 years. So hope in the future year we will going to conduct in the within the 2 years duration of time. The aim of the conference is to bring together international communities, professional scientists, scholars, stakeholders from academic, government sector, industry, and other organizations, and to establish coordination among them for extensive research collaborations. The conference endeavors to discuss and ponders upon new and exciting advances, challenges, and prospects in the advancement of nanoscience and technology, covering field from theory and experiment to application of advanced materials and nanostructure material. This conference will provide platform for many young researchers and students in India and abroad to learn and advancement in the field of nanomaterial sciences. The scientific program of conference will consist of mainly the plenary, keynote, and invited talks by eminent researchers from around the world. We are greatly impressed with the overwhelming response we receive from across the world. And we are happy to announce that around 166 eminent persons and researchers from the different corners of the world are participating in the ICTNMST 2022. This includes 67 poster presentation, 47 oral presentation, 1 keynote speaker, 12 plenary speaker, 23 invited talks. Apart from this, we have an eminent researcher participating as a chairperson. The entire conference will be having 12 different sessions, excluding the 4 poster sessions. And we are happy to announce that we have an eminent researcher from different CEO of nanotech company also, one from Chile and one from India. So they will share the experience for industrialization of the nanotechnology. We express our sincere gratitude to all the participants for their kind cooperation and contribution to this conference. The diversity and high standard of submission we receive for this conference will certainly render the scientific program stimulating and informative. The organizing committee is grateful for the support and valuable suggestions received from many people. Especially, we gratefully acknowledge the encouragement received from honorable members of Scientific Advisory Committee, who also had a task of reviewing the submission we received. We also appreciate with honor the kind of support we received from the supporting journal and publishers. And we are happy to announce that we are going to publish the papers in for two reputed journals, one from Elsevier, one from the Springer. We are also grateful to all the keynote speakers, plenary speaker, invited speakers, session chair, and all our oral and poster presenters for their valuable contribution and support. Organization of ICDMST 2022 is a very much team effort. All the members of organizing committee, working committee, and volunteers have put their best effort for organizing the conference. We particularly wish to pay special thanks to Honorable Director NIT Nagaland, the patron of the organizing committee. And I also just want to thanks to Professor Abhi Ramachandran for his enormous contribution towards this novel effort. He is the person, already I mentioned, initially coined the concept of the DEATH conference. Hope this conference will give the participant a lot of opportunity to explore collaboration, discussion in the current and future trend of nanotechnology research. At last, I just want to extend my welcome to all the participants to this conference. Thank you.
Thank you, Dr. Bora. So I checked it that we have now 31 participants joining us. So I think we'll be joined by them in the coming hours. Now I would like to introduce a very special person among us. So he has already been introduced by Dr. Bora. But then it's my turn now. So Professor V. Ramachandran was the former director of NIT Nagaland, and before joining our institution, he was the Vice Chancellor of Anna University, Trichy. He's now a retired professor from the Department of Information Science and Technology in Anna University, Chennai. He was also the director of Ramanujan Computing Center at Anna University. He has numerous research publications in several reputed national and international journals. His area of research includes cloud computing, web technologies, and Internet of Things. Apart from all the credentials and his contribution towards academia or society at large, this conference would not have started without his cooperation, encouragement, and zeal. So we owe him a lot today, and it gives us immense pleasure to invite him back to his home as the guest of honor of the inaugural program of ICET and MSc 2022. Welcome, sir. Now I'd like to request Professor Ramachandran to share a few words. Thank you.
Thank you. Thank you very much. Yeah. First, am I audible to all of you?
Audible, sir.
Yeah. Yeah. Are you able to see my screen?
Yes, sir. Yes, sir.
Thank you. Thank you. Well, Honorable Director of NIT Nagaland, Professor S. Venugopal, respected Chief Guest, Honorable Director of NIT Arunachal Pradesh.
I'm able to log in to join the meeting. Now, when my turn comes, how do I share?
Professor P. Maganta, respected Honorable Eminent Scientist, Professor D.D. Sharma from IIC Bangalore, the conveners, my colleagues, Dr. Jyoti Prasad Bora and Dr. Amrit Ujari, respected keynote speakers, distinguished professors from our country, from other parts of the world, beloved faculty members of NIT Nagaland, research scholars, participants from India and abroad, and presenters. Good morning to all of you. I hope and pray that all of you and your family are safe and protected. It is a great pleasure and a great privilege to be addressing all of you as guest of honor in this great occasion and to part in the International Conference on Emerging Trends in Nanomaterial Science and Technology. I am truly humbled. I would have been more powerful in a face-to-face setting, but these are unprecedented times, so I will try my best to make this presentation online as much useful as possible for each one of you. Today is a proud moment, not only for the inauguration of this conference in the grounds of NIT Nagaland, but also I came to understand the Chumukadima village where NIT Nagaland is located is now achieved a status of districts. I am really happy to know about this and our heartfelt wishes to all the residents and inmates of the Chumukadima districts. Well, I wish to emphasize there exists a lot of challenges and opportunities for carrying out extensive research, integrating nanoscience and machine learning. That's why I give a small presentation which is titled as Machine Learning in Nanomaterials Research. As I told you, there are a lot of challenges and opportunities, right, for carrying out extensive research, integrating this field with machine learning. And recently, a new hardware is emerging, which is termed as neuromorphic computing hardware, which is actually used to implement machine learning algorithms more effectively. The nanoscience is the foundation for neuromorphic computing. Machine learning shall be connected to nanoscience in three ways. One is machine learning algorithms shall be used to analyze and extract new insights from large nanoscience datasets. There is a website called Kaggle where you can find a lot of nanoscience datasets which will talk about the concept of nanomaterials and nanotechnology. The second challenge, applying machine learning algorithms to accelerate materials discovery with experimental design. The third one is realizing the hardware. As I told you, there is a new hardware coming up, neuromorphic computing hardware, which is actually tailored for machine learning applications using the nanoscience of memory-stive devices and sensors. So these are all the challenges and opportunities the young researchers can focus to develop a lot of research works in this particular area. In general, research on nanotechnology and nanomaterials largely relies on costly experiments and complex calculations, such as density functional theory, whereas machine learning boosts the design and discovery of nanomaterials in a standard way with common procedural steps. Hence, machine learning becomes a powerful tool for nanomaterials research. Machine learning algorithms can address, in this regard, the large amount of time needed and labor consumption in materials testing and achieving big data. Also, there's an opportunity for high throughput screening of nanomaterials. And applications of machine learning algorithms will certainly boost the design and applications of nanomaterials. So the biggest challenge is about large knowledge gap in this area of research and the associated critical issues that should be promptly addressed to promote nanomaterials from laboratory to industry. Hence, it is highly recommended to inculcate research that provides insights for the development of machine learning algorithms in nanomaterials research, especially in the areas of enhancement to the design of nanomaterial structures, their properties, absorption, and catalysis by machine learning, and machine learning predictions of interactions between nanomaterials and nanobiology. Actually, the main concept of machine learning algorithms is normally dealt with data-driven research activities. The major machine learning applications in the field of computational technology or nanotechnologies are property prediction and material discovery. The data-driven research activity in the field of computational nanotechnology is the current requirement and the most emerging field. This massive amount of raw data needs to be stored and interpreted in order to advance material science field. Identifying correlations and patterns from large amounts of data, complex data, shall be performed by machine learning algorithms. Machine learning algorithms shall be developed and implemented to extract knowledge and insights from the accumulated nanomaterials datasets. Ultimately, the data-driven strategies include data mining, data pre-processing and screening, appropriate feature extraction to identify the target attributes for materials discovery and property discovery and property prediction, and the feature selection for developing appropriate model building, and certainly development of appropriate machine learning techniques for efficient model building, right? So definitely, if the young researchers are concentrating on machine learning applications on the nanomaterials research, definitely it will meet the standards of the Industrial 4.0. So with these few words, I hope this 3 days international conference will show how new approaches to modern computational materials science are being used to uncover complexities and design novel materials with enhanced properties. Further, I hope the researchers will certainly observe lots of present research problems, challenges, and potential future perspectives of this new exciting field. I wish the conference great success. Once again, my sincere thanks to the authorities for giving me this opportunity to address this great event. Thank you one and all. Thank you very much.
Sir, for your words and for also for whatever you said related to machine learning. The audiences which are offline here from Nagaland, they are enlightened. And also the participants connecting us over virtually. So thank you so much again, Professor Ramachandran, for being
Thank
here,
you.
for giving your time, for giving your precious time to us. It means a lot to us. Okay, now the chief guest of today's event is Professor P. Mohanta, Director, NIT Arunachal Pradesh. He is a professor in the Department of Mechanical Engineering, IIT Guwahati. Professor Mohanta completed his PhD from IIT Guwahati. His area of specialization includes heat transfer, conjugate radiation, conduction and convection problems from renewable energy, biodiesel, biomass, gasification and biogas technology, from circulating fluidized bed technology to energy conservation, combustion and gasification of solid fuel, and refrigeration and air conditioning. We are honored that he has agreed to be a part of this event. So I would like to request Professor Mohanta to share a few words.
Am I audible?
Yes, sir.
Okay. Just a moment. Namaskar. Professor Venu, Director of NIT Nagaland. patron of this particular conference. Professor Ramachandran, former director of MIT Netherlands and founder of this conference. Professor Vijay, Professor D.D. Sharma of IIT Bangalore, Professor J.B. Purua of IIT Guwahati, Professor Vasudev Siriguri from former UGC DAE Consortium for Scientific Research.
I think his connection got lost. Professor Mahanta's connection. And
Maybe he will be joining.
Mr. Mahanta, can you hear me, sir? Can you hear me?
Yes, yes.
Okay, okay. So
Am I audible? Am I audible now?
Yes, sir, you are. Yeah, you are.
Okay, okay.
Yes, sir, you can continue. Hello, sir. I hope I'm audible to other participants. I think there is some problem. There are some technical glitches.
I think you should inform Professor Mohanta that his connection is lost.
Yes, sir. We'll call him now. We'll do that. Thank you so much, sir.
Pardon?
So
Hello.
we are actually calling him. Our director, sir, is calling him over phone. Sir, Mohanta, sir.
Yes.
Can you hear me now, sir?
Yes, yes, sir.
Sir, your screen is actually not visible.
hear you.
Is there
I
any
can
issue
hear
with
you.
that part? Okay. So you can continue, sir.
Mahanta, you are not audible.
I would like to request all the delegates and the participants to wait for a moment. Professor Mohanta is joining us again. I think these are part of, these are the cons of joining in online session. So I'll ask everyone to have patience.
Not now. Get started.
I think he came back.
Yes, Professor Mohanto sir, can you hear us?
Yes.
Okay, now your video is visible actually.
Okay, thank you. I'm
Okay,
starting.
thank you. Thank you, sir.
I think conference started during the year 2018 in MIT Netherlands, and it is the second edition. I congratulate Professor Ramasundran, an organizer of this conference from the Department of Science and Humanities, namely Dr. Bora, Dr. Pujari, and Dr. Paul Chaudhary. I could see large number of papers are accepted for oral as well as poster presentation during this conference. Regarding this pioneering work from the Philips Feynman, this nano word has come into picture, but it is in the year 1959 actually. Then Professor Norio Taniguchi, professor in Tokyo University in Science, coined the term nanotechnology in the year 1974 for the first time. He described the semiconductor processes such as thin film deposition and ion beam billing exhibiting characteristic control of the order of a nanometer. And nanotechnology, it mainly consists of the processing, separation, consolidation, deformation of material by one atom or one molecule. The word nano means dwarf in Greek. A nanometer is 1 billionth of a meter, or it is 10 to the power of -9 meter. So material having at least one dimension in nanometric scale is termed as nanomaterial. These are all well known to all of you. But a little bit of history I was speaking because in every courses, every subjects, history plays an important role. The invention of scanning tunneling microscope in the year 1981, jointly by Gerd Binning and Henrik Rohrer at IBM Zurich Research Laboratory, followed by the discovery of fullerene in the year 1985, accelerated the field of research and development of nanomaterial and its application. Henrik Rohrer is considered to be the father of nanotechnology. In India, similar role played by Professor C.N.R. Rao, who is the pioneer of nanotechnology in India. The area of nanotechnology, as we can see from the brochure of this particular conference, is incredibly broad and it is interdisciplinary. At the nanoscale, the physical, chemical, biological properties of material differ in an knowable way from the properties of individual atoms and molecules or bulk. This study of this particular technology or science technology requires studies in the field of physics, chemistry, materials, even now biology. If you go for technology orientation, application of nanomaterial is becoming very important. Application is in fact it is countless, starting from cosmetics, nanofabrics, bioengineering, defense and security, optical engineering, robotics, nano devices, nanobiotechnology, medicine and drugs, even energy storage are becoming important for this particular branch. The oldest technology was silver nano platform for using silver nanoparticle as an antibacterial agent, nanoparticle-based transparent sunscreen, and carbon nanotube for stain-resistant textiles are some examples of application. One of the wonders in nanomaterial is the development of food or nanotube. The material exhibits high strength to weight ratio, so it goes for the immediate application for lightweight spacecraft. Further, carbon nanotube application lies with cancer treatment due to its ease for penetration to the biological cell of the wall. Moreover, electric resistance change when other molecules attach themselves with the carbon atom. This principle is engineered in making sensor for detecting chemical vapor in atmosphere or other environment. Other applications are like making bicycle body. For example, Eastern Bell Company, lightweight boats, electric cables and wires, solar cell fabrics, etc. etc. Nanorods or quantum dots within the range of 1 to 100 nanometer. Cancer therapy, micro electromechanical systems like MEMS has got a lot of application. It has got wide application in display technology also, because the reflectivity of the rods can be changed by changing their orientation when applied to an electric field. Further, the nanobots are close to 10 to the power minus 9 and are still under R&D. It's tried with engineering applications such as drug delivery, biomedical applications, detection of toxic compound in environmental. Coming back, actually IIT Bombay started nanotechnological aspect and material science, nanomaterial science in 2000s. Soon after that, Government of India started Nano Science and Technology Mission in the year 2001. In the year 2007, this mission was allocated with rupees 1,000 crore to promote nanotechnology-based R&D with basic research promoting the specialization, infrastructure development to carry out front-rank research, development of nanotechnology and application, human resource development, international collaboration, etc. Many institutions in India are offering PhD and master's programs such as ISC Bangalore, IIT Bombay, IIT Guwahati, and few NITs also have started these programs. Further, lies with the development of lighter and stronger programmable material that requires less energy, greater fuel efficiency on land transport, ship, boat, aircraft, and space vehicles. Use of nanorobotics is also in an important area for research and development in future. This can be very useful when human cannot accomplish a task. Even it may be useful to rebuild the depletion of ozone hole. Nanosurgery may be taking a lead in critical surgical operations in future. Hence, my earnest request to all the participants that knowledge sharing is one way. Making a group consisting of physicists, chemists, biotechnologists, physicians, and engineers is becoming important. So ultimately, we require collaboration, hand-holding of each other. So collaboration is also important in nano material and nano science and technology, because the instrument costs or equipment costs are very high. A small R&D lab cannot afford that kind of devices. So there are some premier institutes like IIT Bombay, IIT Guwahati, or that kind of institutions who are having these kind of facilities. So the small institutes can always collaborate with this kind of premier institutes, even foreign universities, foreign institutes. This becomes very important. So the end of this conference, I think it will lead for a collaborative research for all the like-minded researchers. This will help not only in developing nanomaterial, but also will help in product development, lab to land, and Dr. Professor Ramasandran was telling. That becomes important nowadays. India today requires indigenous product development for self-sufficiency, for creating own job, and to increase net GDP. Hence, this platform will be help the participant perhaps in achieving this goal. So I congratulate all of you for taking the initiative, and I sincerely thank all of you again. Thank you. Jai Hind. Namaskar.
Thank you, sir.
Thank you.
Thank you so much, sir, for your kind words. It is actually an opportunity for all the students of this host institute, NIT Nagaland. It is an opportunity for us to learn so many things. Apart from that, to get inspired. The professors who are going to join us for these 3 consecutive days, they will be inspiring us a lot with their work, with the novelty of their work, whatever they are doing in their field, with the position that they are holding. It is a bright chance for all of us get inspired, and we can just hope that someday some of us, some among us can be in their position. So it's a big dream for all of us, for me as well. So with that, we are coming to the end of today's inaugural program. We are now joined by the keynote speakers, the invited speakers of today's program. Professor D.D. Sharma has already joined us. He has joined us. And I think I have seen, we have also seen that Professor V.S. Vallabhapurapu from University of South Africa, he has also joined us. So welcome to the session, sir. And another plenary speaker is also there. He will be joining us from Spain. He has not joined us yet, probably because of the time difference. He'll be there with us, joining us shortly. At the end of the session, we have two programs left. The first one is that I would like to request the convener, another convener of ICET NMST 2022, Dr. Pujari. He's also the Dean Academic of NIT Nagaland. So I would like to request Pujari sir to give the vote of thanks on behalf of the organizing committee. Sir.
A very good morning to all of you. Respected Chief Guest, Professor Pinakeshwar Mahanta, Guest of Honor, Professor V. Ramachandran, respected Professor D.D. Sharma from IIT Bangalore, Professor J.B. Borua from IIT Guwahati, Professor Srinivasalu from University of South Africa, Professor Basudev Siruguri, Deans and Associate Deans of NIT Nagaland, respected faculty members, Honorable Director Professor S. Venugopals, and respected participants. On behalf of the organizing committee, I feel privileged to propose the vote of thanks for the inaugural session of ICET NMST 2022. So we'd like to extend a very hearty vote of thanks to all the dignitaries present in the inaugural session today. We are specifically indebted to Professor Pinakeshwar Mahanta, the chief guest of today's program, and Director NIT Arunachal Pradesh, for your insightful and most stimulating speech. So we are very much grateful, sir, that you were kind enough to take the time out from your busy schedule of works to attend this inaugural session. We are equally grateful to Professor V. Ramachandran, Guest of Honor and former Director in NIT Nagaland, for his valuable time and for your eloquent speech. As rightly mentioned by Dr. Bora, he was the pioneer of this international conference, and maybe it will not be wrong to say that it was the brainchild of Professor V. Ramachandran to organize such a wonderful international conference here at NIT Nagaland. I am glad to mention that his involvement and motivation during the first series of conference in 2017 was really praiseworthy. And even till today, he is motivating us time to time with his valuable suggestions. So we are very much thankful to you, sir. We extend our sincere thanks to all the dignitaries and eminent research scientists from different corners of the world and different parts of India for attending this inaugural program by managing your busy schedule of works, and also for your suggestions we received time to time during the initial preparations of the conference activities. We are thankful to entire NIT Nagaland administrative staff, as well as Dr. R.P. Acharya, Registrar in charge NIT Nagaland, Deans, Associate Deans, and faculty members, staff members, for their enormous efforts in making this event a successful one. Specifically, the contribution and support you received from data center kind of peoples like Vikas Sharma and Mathivanan is really praiseworthy. As well as we also thank Mr. Papu Sharma for his support during the initial preparation of our work. We must have to acknowledge the support received from the research scholars from Physics and Chemistry Department and NIT Nagaland for their endless dedicated effort under the able leadership of Dr. J.P. Bora. Finally, we extend our sincere thanks to all for being with us during this entire program. Thank you. Jai Hind.
Thank you so much, sir. We have come to the end of the inaugural program. So we'll end it on a good note by singing the national anthem of our country. So I'd like to request everyone in-house to stand up. And I'd like to request the MSc students from Department of Physics to initiate the anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तब शुभ नामे जागे तब शुभ आशीष मांगे गाए तब जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
Everyone can take their seat. Thank you so much. So we'll continue with the keynote session. Now I'd like to request the convener to take the floor. And the inaugural session here comes to an end. So thank you so much, everyone. The participants who joined us throughout the inaugural session. I think we have 42, around 45 participants now. At the end, we'd like to do one thing. So every conference we take pictures, right? But now, since it's online, we'd like to request everyone to switch on their mic. The delegates has already been switching on their mics from the morning. A video, sorry, switch on their camera. So we'll take a picture. We'll request all the participants from NIT to come forward. We'll take a picture and that would be captured. That would be a screenshot actually. So I would like to request all the participants to switch on their cameras. So we can now see the faces of the participants. Hopefully if it was offline, we could have seen you in here. So I'd really like to request everyone. The delegates, they're really waiting for you. The scientists are waiting for you. So the young researchers, I request everyone. So we have some people from even conference hall. They have opened their camera as well. So yes, we have more people coming here. Thank you so much, Sharma sir, Didi Sharma sir. I could see smiles on your face. Professor Siruguri sir, thank you so much. So we'll need smile as well, okay? We'll request everyone to give their beautiful, precious smile as well. We can see Professor Vallabha Purapu, sir. So thank you for joining us again. I think we are ready. So everyone is ready, right? So on a count of 1, 2, 3, the picture would be clicked. So everyone can please show their precious smile. Okay, thank you. So it's on a count of 1, 2, 3. Yes, you can unmask yourself as well if you want. Ready? Okay. So on a count of 1, 2, 3. I think, are we done, sir? Done. Okay. Thank you so much, everyone. Thank you. Thank you so much. Okay. Now I'll give over the stage to Dr. JP Bora, convener of ICT and MST 2022. My work is done here, so I hope I did a good job. Now it's over to Professor Bora. Thank you. Thank you, sir. Thank you so much for coming.
So now the inaugural session is finished. Thank you for nicely conducting the and compare the session by the Sarodi. And now we'll have the main core session. We are going to start the core session. And there will be 3 talks that followed by 1 keynote speaker, Professor D.D. Sharma sir. And after that, the Professor Srinivasu sir from the University of South Africa, and Professor Jos Barandian from Spain. So the talk will be starting from the Professor D.D. Sharma sir, and thank you, sir, for accepting our invitation, even though you have a busy schedule. So at least you have managed the time for your talk in our conference. Thank you, sir. So I just want to brief about his biography, and I think all the nanotechnologists know about the Professor D.D. Sharma, sir. And in the last conference, he was given a very enlightened talk, and he was enlightened to all the participants, and he came by physically because at that time there is no pandemic and all those things. So we listen by physically. So even now, this conference in the hybrid mode and in the online mode, I think sir will enlighten us also. So sir is basically from ISC Bangalore, and he's completed his MSc degree in physics from IIT Kanpur in 1977, and a PhD degree in 1982 from ISC Bangalore, and he worked in Canforce, it is in Zurich, Germany, as a visiting scientist during 84 to 86. Sorry for not pronouncing this one, it's a German place. He was a faculty member at Solid State of Structural Chemistry Unit of ISC Bangalore during 86 and 21, and he was the first holder of the Tata Chair of ISC during 17 to 20. He is now serving as an honorary professor and CSR Bhatnagar Fellow at ISC. His research interest spans the science of strongly correlated electron system, primarily based on transition metal compounds, semiconductor nanocrystal, and energy materials using a wide range of experimental and theoretical tools. He has published about 500 scientific papers and holds several patents. He is an elected fellow of 3 Indian science academies, the Engineering Academies in India, the World Academy of Science, and the American Physical Society. He has received many national and international awards and recognition, including multiple honoris causa doctorate degree. He has held several academic positions outside his parent organization, including many honorary guest visiting professorship, such as Gaspard Mock visiting professor at Ecolo Polytechnic, University Professor of Computational Material Science, University of Vienna in May 2017, Guest Professor of Physics, Uppsala University from 11 to 16, Visiting Professor at Department of Complexity Science and Engineering, University of Tokyo during 2001 to 2002, Distinguished Scientist at CSR 11 to 16, MLS Chair Professor at ISES 2006 to 9, Adjacent Professor at TFR, 2003 to 2009 and 2011 to 2014, Honorary Professor at JNCSR, and SNB and CBS, and Distinguished Visiting Professor and Eminent Visiting Fellow at ISES. So, such eminent person, so giving the talk, so I think definitely we will get all the audience and the participant will get benefit. So, I just want to give a time to sir. Hello, sir.
Thank you.
Yes, sir.
Can you hear me?
Yes, sir. Yes, sir. You can hear you, sir.
Thank you very much, Professor Bora, for a very kind and long introduction, which even delayed us to start the program, but very kind of you. I very fondly remember my last visit to NIT Nagaland, and I was really hoping that I'll be able to come in person this time. If you remember, in our discussion, I had promised that I will definitely come. If this Omicron variant new surge hadn't come, I would be with you. And I hope that in the next edition of your conference, I'll be able to visit again, because I have very fond memories of visiting the place as well as interacting with students and faculty there. Let me start my talk by thanking the organizers, in particular Professor Bora and Professor Pujari, conveners of ICTNMST 2022, for inviting me to this particular program and to give my talk. Thanks also to the dignitaries, Professor Venugopal, Professor Ramachandran, Professor Mahanta, Dr. Vasudev Siruguri, and many other colleagues of mine, as well as students, to be attending this talk. Let me start by sharing, and let me hope that I can do that right. And tell me that if you can see my screen. Do you see my screen? Can you see my screen? Can somebody confirm?
Yes, sir, we can see.
Yes, sir. Yes, sir. We can see your screen.
Wonderful.
Yes, yes, we can see.
Okay. So, and I'll use the cursor to point to. So the talk that I have promised to give is the layer resolved electronic structure. It's a very long title. Forget about the title. I'll focus on what I'm going to talk about and slowly break it down and build up the story to tell you where the excitement is in this particular field. Before I do so, it's my pleasure to acknowledge the support, the financial support that we have got over the years, which have enabled us to do this research. Because the research that I'm going to present to you has input from years of research, decades of research, and over these many, many decades of involvement in science, we have been supported very generously by Nanomission, ACRB, DST, all various wings of Government of India, as well as by Government of Sweden in the early years through the Swedish Foundation for International Cooperation in Research and Higher Education. I was also very fortunate to have this private funding of Jamshedji Tata Trust for 3 years, very generously supporting our research. And now at present, we're supported very generously again by CSIR and Bhatnagar Fellowship. The plan of the talk is going to be, and this being I think 50-minute talk, I'll talk for about 45 minutes and leave about 5 minutes or a little more for the discussion at the end. I'll talk a little bit of the challenges. What are the difficulties? What are the kind of issues that you're going to ask? Then I'll tell you what the technique that you're going to use to address those challenges, those difficult questions. And then I'll illustrate how powerful this technique is by applying it to two specific cases. One is known as the lanthanum aluminate strontium titanate heterostructure, and the other is strontium titanate lanthanum titanate heterostructure. Whenever I talk about a heterostructure, let me start by explaining the challenge to you. A heterostructure essentially means that there are two different components. Hetero refers to that. It's not a homogeneous structure. There are two different units. And these two different units are in contact with each other, and that defines an interface. What do I mean? Think of a material A and a material B that are in contact with each other. The interface is this line of contact or plane of contact between material A and B. So the interface itself has no volume associated with it. It's literally the plane that connects A and B. On one side of the interface, you have material A. On the other side, you have material B. And the question is, should this interface matter? It turns out that this interface controls the properties of many, many materials. So here you have something called that interface, which has no volume. It's only an area, a contact plane between two different materials that control the property of the material, and I'll show you how that happens. And it gives rise to non-trivial properties that the interface property is totally different from the property of A or property of B. And that's when one is excited, and those are the kind of examples I'll take and to explain to you. Remember, if I take two pieces of A and join them together, of course, there is no interface. So the interface necessarily requires two different materials that will connect to each other, and this is what we're going to study. Does that happen? I mean, truly, such a thing can one make? I'll give you an example. What you're looking at is actually the system that I'll be talking about later, this lanthanum aluminate strontium titanate, which you also call LaO for lanthanum aluminate, STO for strontium titanate. And you're looking at a cross-sectional TEM image, where you can see that the lattice parameters, these are the columns of atoms that you're seeing, over here is due to STO, this part. And the top part, these 6 layers that you see in a slightly different atomic arrangement, is the lanthanum aluminate. So you have lanthanum aluminate on top, strontium titanate below, and that's your interface. And you can see how beautifully the interface forms, which is just the contact plane between the lanthanum aluminate and strontium titanate. And later in the talk, I'll tell you how it modifies the properties of lanthanum aluminate and strontium titanate, not quantitatively, but qualitatively, and why does it happen, and how we go about trying to understand that. But immediately you'll realize the difficulty when you're interested in properties that arise completely from the interface alone, because after all, the interface appears at a depth, right? Because there is another material on top, A, and you have to look through A to reach the interface which you are interested in. And also the interface is very thin. Ideally, it's of 0-dimensional in the perpendicular direction. So any technique that averages over volume to give you the property will not have any sensitivity because an interface has no volume. So strictly speaking. So you need to have something that will be able to have a microscopic ability to be sensitive only to the interface layer and therefore tell you what the properties are. So you need a microscopic technique. You need a spatial resolution that would be able to focus down onto that particular layer that is called the interface and tell you what the properties are. Remember the normal microscope that we talk about, TEM, SEM, AFM, STM, all these microscopes actually give you a lateral resolution. But here you need a vertical resolution. You need to go vertically into the material and then understand the property of that TM, of that interface. That's why when we looked at the transmission electron microscope picture that I showed you, we had to do a cross-sectional cut to see again from the side, because I can only have lateral resolution with a microscope. And so in order to see the interface, I had to make a cut perpendicular to the interface and then look at that surface. And that is invasive. I have to cut the material. I don't want to do that because when I cut, I actually introduce yet another interface, which is between the material and the vacuum. And that may change the property of the interface. So I don't want to cut the material. I want to look inside without any invasive way. So we need a non-invasive technique. And I'll show you how this can be done using high energy photoemission. Photoemission is not normally used for microscopic technique. And I'll show you why photoemission is exquisitely suited for this particular purpose. And it has a tunable surface sensitivity. Let me tell you in a moment how we do that. And that brings me to this technique employed. And photoelectron spectroscopy, all of you know what it does. This, what I'm showing you over here, is the electron states in a material, a metal, Fermi energy there, and these all states are occupied. This is the valence band region. These are the core levels. I come in with monochromatic photons, H nu energy, and the electron absorbs that energy and gets kicked out into continuum. I measure the kinetic energy of this electron, reference to the Fermi energy. You can see that the energy conservation tells me that the photon energy from the state I pull out to the state that I go, that kinetic energy, this entire energy is the photon energy because the photon energy has been absorbed. That energy is split between two parts, the kinetic energy that I measure and the binding energy that the electron had. So the energy conservation tells me that H nu must be equal to kinetic energy plus binding energy. Since I can measure the kinetic energy and the photon energy is known to me, I can reverse this equation to say H nu minus kinetic energy is the binding energy. And so I can find out the binding energy and map out the electron states this way. There are subtleties that I'm not going to, I'll jump across that and come to this equation that I just now told you, that the kinetic energy is equal to the photon energy minus the binding energy. Now, binding energy of any level is fixed in a material. But I can change the photon energy. If I change the photon energy, for example, using a synchrotron source, I'll be changing the kinetic energy. And as I change the kinetic energy, the electron's ability to come out of the material, remember, I cannot measure the kinetic energy of the electron unless the electron comes out of the material. Once it comes out of the material, I can catch it and measure its kinetic energy. So it has to come out. The ability of an electron to come out depends on the kinetic energy that it has. And this plot over here is telling you what is the probability, which we express in terms of an average depth from which an electron can come out without suffering an inelastic process as a function of the kinetic energy of the electron. Since we'll be operating with high kinetic energy, do not worry about this part of the plot. So we are in this regime where you can see as I increase the kinetic energy, the ability of the electron to come out from greater depth increases. What is the implication? Now think of that you have two materials, a homogeneous alloy and a graded alloy whose composition changes in this direction as shown by the color. And I'm going to look from top and do photo emission. So I start with photo emission with very low energy. Now when I have very low photon energy, kinetic energy is low, electrons are coming out only from the top layer. And I measure what the composition is because I know which are the elements contributing by looking at the core levels. Now I increase the photon energy a little. What happens? Kinetic energy increases. So I start to get information from further down. As I systematically increase the photon energy, I keep looking deeper and deeper inside. Not because of photon penetrating. Photon penetrates through the material much more distance, but the electron that I'm interested in cannot come out without suffering inelastic loss. And I change the kinetic energy of that electron by increasing the photon energy, and therefore I'm taking slices. And in these slices, suppose this yellow is my interface layer, then I can look at photon energy with this and the photon energy with this, and what additional information I get essentially comes from that interface layer. And that's how we can study the interface with tremendous sensitivity. The question is, do I really have this sensitivity? We've published series of papers. This is the technique we introduced way back in 1999, and we've been using it over the years. And there are many, many different applications that we have shown. But the question is, this is all conceptual. Does the spectrum actually change when I change the photon energy? Because if it didn't change, that means I have no sensitivity. I'll show you one quick example that we had published long time back using some nanoparticles, lead selenide, which was covered with an organic unit which had phosphorus in it, topo. And phosphorus that couples to the nanoparticle because of chemical binding has a different binding energy. And if there's a physically absorbed phosphorus on top, that'll have a different binding energy. And you see, as I change the photon energy, 200 eV, 600 eV, 800 eV, and 1.5 keV, the spectrum changes very drastically. There are many components. This is the physically absorbed outer layer phosphorus. This is the phosphorus coming from the chemically absorbed on the surface. And these are the lead signals. There are two components of lead signal, the surface lead that couples to the phosphorus and deeper lead that does not couple to the phosphorus. And then you can analyze this data to figure out exactly how the structure is. And you have used it tremendously for understanding the structure of nanomaterials, but I'll not be talking about that today. Let me get back what I've promised to talk about, which is the lanthanum aluminate strontium titanate interface. Why should anybody be interested? This is the cross-sectional TEM that I had shown you earlier. I told you we have strontium titanate here, lanthanum aluminate there. Now, strontium titanate is a high band gap insulator, D0 system. It has no magnetism. Lanthanum aluminate is an even higher band gap material, no free electron, no magnetism. When I create this interface, it turns out that what I see is a very high mobility metal, which can even show superconductivity under certain circumstances and magnetism in certain other circumstances. And then you can see that you take two materials which are very high band gap material, completely boring in the sense of metallicity or magnetism. You make an interface between them, and suddenly you find the material is showing signs of being a high mobility metal, superconductivity and magnetism. And that must come from this interface, which is why suddenly I see this effect, which wasn't there before. Now, let me tell you how people have tried to understand this phenomenon. The way we have tried to understand this phenomena, and this is just a resistivity plot to show you that indeed the interface is metallic, highly metallic, nominally metallic, because as I lower the temperature, you can see that the resistivity is coming down. Now, this is strontium titanate structure, lanthanum aluminate structure. You can see that this is a strontium oxide layer, SRO layer. And this is the next TiO2 layer, SRO layer, TiO2 layer. That's how strontium titanate is built. And you can see strontium 2 plus oxygen 2 minus is a charge neutral layer. Since this 0 shows what is the effective charge of this layer. So this is made of all charge neutral layers. But if I look at lanthanum aluminate, which on an average is charge neutral, but this LAO layer, because lanthanum is 3 plus and oxygen is 2 minus, has a positive charge. This aluminium 2 oxygen has a negative charge, positive charge, negative charge. So I have positive charge layers and negative charge layers alternating with each other in the lanthanum aluminate. And this is the overlay that I am making, and I truncate it after a few layers. What is the implication of that? You can see now it's schematically shown. These are all charge neutral strontium titanate layer. Then I have a positive, negative charge density. And that gives rise to an electric field, which looks like this. And this electric field, when you convert it into a potential, looks like a potential that's running away, becoming stronger and stronger as you build up this layer. And that electric field would affect the electron states. And what would happen in strontium titanate, where there is no electric field, is flat. There's a valence band, that's a conduction band. But lanthanum aluminate, as you grow the thicker layer of lanthanum aluminate, this potential acts on it. The valence band keeps moving up, conduction band keeps moving up. And you can see as soon as this occupied valence band crosses the Fermi level for a certain thickness, it is above the empty level of the conduction band of strontium titanate. And so electron will move from lanthanum aluminate valence band to the conduction band of strontium titanate. And that charge transfer is shown over here. And it is known that if you transfer half an electron per unit cell to this interface, now that interface titanium is no more titanium 4 plus, but titanium 3.5 plus. Now you have half a positive negative charge here, then positive, negative, electric field looks like this, and the potential is controlled and is not diverging. So this is called the catastrophe, polar catastrophe. This is known as polar catastrophe, where the potential grows up, drives an electron, half an electron per unit cell to come to the interface, giving rise to stability. So immediately you can see this half electron dope per titanium would make this system mobile electron, so metallic. Titanium, strontium titanate was non-metallic insulating because it was titanium 4 plus, no d electron. Now you have got d electrons and they are stuck here, and so they can move around, giving rise to a metal. If that be so, are there any questions? It turns out there are many questions, and several questions that you are going to ask, and I'll come to them one by one. That is polar catastrophe that I told you about just now is enough. We know that oxygen vacancies play a role. What kind of role it plays? Is there any, I'm making this interface and I'm assuming this interface to be atomically sharp, but I can have strontium and lanthanum or going across the interface. For example, I know if strontium titanate is doped with lanthanum, it becomes metallic. And so is there an intermixing that I cannot see with transmission electron microscope. Then this argument about polar catastrophe will give me a very thin layer of electron gas right at the interface. Is that all? Or is there a thickness associated with it? That means, where is this electron gas located? And what gives rise to magnetism and superconductivity? In fact, this plot tells you that oxygen vacancy must play a role. Why? Here are different samples. This is the resistance versus temperature. And you can see resistance versus temperature can be varied from lower than 10 to the power minus 2 to up to nearly 10 to the power 5 by 7 orders of magnitude. What is different between these materials? Nothing but the oxygen partial pressure that was maintained or used for annealing when you are making the sample in your ultra-high vacuum chamber. That means oxygen partial pressure available at the time of making the sample dictates 7 orders of magnitude change in the resistivity, which means that the oxygen vacancy must play a very important role. The fact that you can change the carrier concentration so extensively also tells you that oxygen vacancy must play a role. Polar catastrophe, since it contributes only half an electron per titanium, we know its exact concentration. It should be 3 to 10 to the power 14 per square centimeter. Whereas here we can go from lower to much higher. So oxygen deficiency plays a role. Is there an intermixing of lanthanum and strontium? Now also, if you look in more detail at the nature of the conducting carriers, it turns out, I'll not spend too much time on it, it appears that there are 2 different kinds of carriers. One carrier, large density, low mobility. Another is low mobility, a high mobility, but large carrier density. Where are these coming from? Why do you have signature of different kind of carrier concentrations? So these are the questions that I'm going to ask. And how do I go around asking this question? We are going to look at the core levels, monitor the core level, looking down from top with photo emission. This is a paper that we published way back in 2016 and was mainly driven by Shumanta Mukherjee, a PhD student at that time, and 2 other people, Banaveer Paul, who's now with Stuart Parkin in Halle, and Debra Chaudhary, who is a faculty member at IIT Kharagpur, and held by many people, international collaboration. This is done, some of the experiment was done at German Synchrotrons Center, Wolfgang Grube and Internil Sarkar. Some were done in Bessie, Germany. Mihaela Gorgoy was our partner there. Ulof Karis from Uppsala University, and Hide Takagi and Jobu Matsuno from Japan. Hide is now at MPS Stuttgart. What we are going to look at is this planar structure looking from top, and we'll change the photon energy and successively look deeper inside as we increase the photon energy. And if the composition changes, like here, the blue element and the red element, the blue element is lanthanum of lanthanum aluminate, red element, red is strontium of strontium titanate. And I'll keep looking deeper inside. As I increase the photon energy, I'll begin to see more and more the red element. By analyzing this, I'll know how sharp the interface is. So lanthanum on top, strontium titanate, lanthanum core level looks like this, strontium like this. I'm going to plot the intensity ratio of lanthanum divided by strontium, which will go down as I increase the photon energy because I look deeper inside, so I increase strontium. And you can see indeed from 2 or 3 different samples, the intensity ratio of lanthanum to strontium decreases as I increase the photon energy. So I know that lanthanum on top, strontium below. Now I can analyze this quantitatively. I can calculate what is the expected variation if I have a sharp interface of X thickness of lanthanum aluminate on top. For example, if I assume I have 2.9 nanometer thick lanthanum aluminate, the intensity variation should have been like this. If I assume that the lanthanum aluminate thickness is 2.6 nanometer, then the variation should be like this. And you can see that the variation is between this 2.9 nanometer and 2.6 nanometer, which means I can determine the interface with an accuracy of better than 0.15 nanometer. That is 1.5 angstrom, which is sub-unit cell. In fact, we believe that you can determine the interface with better accuracy, pinning it between 0.1 nanometer, which means plus minus 0.05 or 0.5 angstrom accuracy. And we do that, and then we fit that, and we find that the thickness, the interface is very sharp, has a thickness of about 2.75 nanometer, and the mixing is less than 1 unit cell, if there is any mixing. But absolutely sharp interface is consistent with our result. Then we ask the question, where are these doped electrons then? Now the doped electrons, I told you, will go into the titanium. And titanium 4 plus will become titanium 3 plus. And as soon as titanium 3 plus, it has a different core level signal in titanium 2p. The strontium titanate gives me this big peak here, which is titanium 4 plus. And in my sample where this doping takes place, I also see the titanium 3 plus signal here. So now I can look at the intensity of this signal divided by that signal. And therefore, I know where this titanium 3 plus is, which means where the electron gas is. I can map out the electron gas in my device by looking deeper down by changing the photon energy. And that's what I'm going to do. When I do that, I can figure out the intensities and plot the intensity ratio of titanium 3 plus by titanium 4 plus as a function of photon energy for two different overlayer of lanthanum aluminate. One is a 6 unit cell lanthanum aluminate, and there's a 4 unit cell lanthanum aluminate. We apply the technique on different samples so that we know that we're doing things right. Now we're going to try and simulate the data for this kind of variation, taking different model distribution of titanium 3 plus or the electron gas. If I assume that there is only one kind of distribution, and that distribution is starting from the interface and a constant density, then the best fit I can get theoretically simulated is this black curve, whereas the experiment is the red one. Which means I cannot fit my experimental data by assuming an electron gas that tied to the interface of any thickness. I can say, okay, let's forget about the interface. Put it anywhere in the strontium titanate. If I assume that, then the best fit I get is this, which again cannot explain the experimental data. That means there are two different kinds of distributions. So I say, okay, now take two different distributions, one tied to the interface, one anywhere in the strontium titanate. Can I fit the data? It turns out that now I can fit the experimental data, which are the symbols, and this is the fit that I'm showing you. And the model that fits it well is a narrow distribution. So this is the sample. This is the gray part is lanthanum aluminate thickness. This is the sharp interface, and this is the strontium titanate. And in blue, I'm showing you how the electron gas is distributed. There's a high density electron gas of the order 2 into 10 to the power 14 per square centimeter tied to the interface of thickness about less than a nanometer. And there's a low density distribution throughout the strontium titanate of about 0.06 electrons per unit cell doped in strontium titanate. And that happens for both the samples that you are looking at, and the description is very similar between the two. Now one then asks the question, where is this distribution of strontium titanate doping coming? What is the origin of it? This is where we ask the question, what is oxygen vacancy doing? And there's a way that we can also find out what oxygen vacancy, how it is distributed. And we look at the distribution of oxygen vacancy, and I'm giving you the final conclusion about it. We find that while the electron density is distributed as shown in the blue, that is a part that is connected to the interface, and a constant distribution throughout strontium titanate, the oxygen vacancy, they also needs two components. One is distributed throughout the strontium titanate uniformly, and another in the top layer of lanthanum aluminate. And it turns out that the oxygen vacancy in the top layer of lanthanum aluminate is just enough to dope these electrons at the interface. And the oxygen vacancy that is distributed throughout the strontium titanate is just enough to dope this electron gas that is distributed throughout strontium titanate. So this is coupled to the oxygen vacancies in this particular material, giving rise to two different kinds of distributions, and that what controls the properties. I'll very quickly show you that we also can understand the property of this electron gas. Is it a strongly correlated? Can it give rise to magnetism? Can it give rise to superconductivity? Does it show any evidence of correlation? That is the question that we had asked. And this is a paper that was published by Shumanto further down in 2018, again in collaboration with these people. These are theoretical support that came from Zilke and Ambroise from France. So we looked at the valence band. Now, valence band is a very difficult thing to look at. So far, I'm telling you everything by looking at the core levels. You can see fairly intense peak, but that intense peak comes from oxygen 2p. This titanium doped electrons are the signature here. You can see there's hardly any intensity. So it's incredibly difficult to experiment. And I've been very fortunate to have very good students, and they patiently collected the data there and they extracted what it looks like. When you expand this very low intensity, you see, I can see what is the nature of those titanium 3D state near the conduction band, valence band. And by changing the photon energy, I see some changes. But that is also, there's a changing background, changing resolution. When we correct for all these things, it turns out that both these photon energies show the titanium 3D spectrum almost identical. That means that the charge density that is tied to the interface and the charge density that is throughout strontium titanate have similar spectral features. They're not very different, except for the fact the one that is tied to the interface is a two-dimensional electron gas, whereas the one that is distributed throughout is a three-dimensional electron gas. And then we try to understand the nature of this peak and that peak. There are two different contributions, what we call the coherent feature and the incoherent feature. And that turns out that I'll not go into the details of it. When you look at it, this part and that part, this part we can understand in terms of slightly correlated, lightly doped titanium 3D electron, but this is the one that cannot be understood in that term. And our guess really is that it is not a correlation-driven feature, so it cannot be associated with the lower Hubbard band. It's not a plasmonic replica. It is most likely vacancy-induced states that are tied to the vacancy, causing polaron formation. So a large part of the doped electron gas is actually not available for the transport phenomena, and they get tied down to the vacancies getting localized. With that, let me stop this part, and the remaining about 10 minutes I'll spend on the other system that I've promised to tell you, which is on lanthanum titanate, strontium titanate. I think there are some microphones open. If somebody wants to ask a question, you're welcome. Otherwise, you can please mute yourself. Now, the difference, why am I repeating my science on yet another system that looks the same? The strontium titanate is common. Instead of titanium, I had aluminium there. The reason being that lanthanum aluminate and strontium titanate, I told you, both are band insulated. But lanthanum titanate is titanium 3+. So it has d electron, and yet it's an insulator. And it's a classic insulator, which is known as Mott insulator. Its insulating state comes from correlation effect. So here, as I told you, correlation effect plays very little role in controlling the electronic properties. But here, a priori, by taking a Mott insulator, I know correlation effect plays a very important role. And now I'm going to make an interface and ask the question, what happens in this case? Because I'm assured to have different physics, because correlation plays an important role. This is the work that was driven by Banavir Pal, who finished his PhD, and two other people, Shyamashis Das and Sumanta Mukherjee, who were PhD students at that time, but since then they've completed. This work is unpublished, and hopefully it will be publishing it soon. Banavir is now postdocing with Stuart Parkin in Halle. And it's again a collaboration. The samples came from University of Arkansas, from Jack, and Jack is now at Rutgers with his group, as well as the experiments were done at Petra, Uzgan Dubey and Indranil Sarkar. Indranil is now in Mohali INST. The reason we looked at it, there were theoretical predictions about this system and what one may expect from this. The theoretical prediction, one of the early ones from Okamoto and Millis, talked about this system, and what they're showing you is the layer resolved electronic structure. The layer, this part is strontium titanate, and this part is LTO, and this is the interface layer. And what they showed that the electronic structure actually changes quite a lot across the layer in many ways. For example, this part, which we call the lower Hubbard band or the correlation induced feature, you can see its intensity is very small at the interface and it becomes larger as you go away from the interface. And on that side, it has no signature. And this part, which is the coherent part responsible for the metallic transport, rapidly decreases as you go inside the LTO, which is the Mott insulating phase. And strontium titanate, which is the band insulator, has a large coherent intensity. This is the Fermi energy, large occupied part, but that slowly shifts up. And very soon you have no intensity, no electrons doped in strontium titanate as you move away. But then there are other predictions, for example, here. This said that the coherent part doesn't change in energy, but changes in intensity. The incoherent part, that is the incoherent part. The coherent part also changes in intensity, but doesn't change in position. But this work showed that very rapid change, that is exactly, there's a coherent part here and here. But if you go slightly further away, there's no coherent signature, and the incoherent part intensity, the energy position changes very drastically. Very different description from here. There are other descriptions, I'll not go into all that, but there are different claims on the system, and so we wanted to understand. This is the structure we are talking about, lanthanum titanate, Mott insulator, on which we grow strontium titanate. This is the valence band with different photon energies, and you can see there's hardly any change at all as you look down from strontium titanate into the system. That's because we are looking at oxygen 2p. I told you there's oxygen 2p. What we are interested in actually states that are lying down here, very low intensity. And so it becomes even more difficult to experiment. When we expand that part, we see that there are structures, and those structures are changing with photon energy. And this change in the spectral shape is what we are going to analyze. And you can also see that the intensity is growing as I increase the photon energy. First, I look at the intensity of this part, the d electron, divided by oxygen 2p as the reference. When I look at that titanium 3D by oxygen 2p, I find that it is increasing. And I can analyze this data to say how titanium 3D is distributed as a function of depth as I look inside. When I do that analysis, I find that titanium 3D, this is the interface. This is strontium titanate. This is lanthanum titanate. And close to the interface, I see that the system strontium titanate gets doped with electron becoming conducting. And that doped electrons comes from lanthanum titanate, which depletes in electron. This is the one electron that I expect lanthanum titanate to have. But you can see that it depletes itself. Some of the electron from here gets doped onto that side. Then we can ask the question, okay, now what is the character of these electrons? What is the correlation-driven features in that? Can I understand that? I told you that, yes, this is the coherent feature, and this peak bump here is the incoherent feature. This comes from metallicity, and this comes from correlation induced. And I can analyze the relative intensity of these two as a function of the photon energy and map out how layer by layer the correlation intensity is increasing or decreasing, or the coherent feature is increasing or decreasing. And that is what I'm going to do now, telling you with respect to interface, how the electronic structure is changing. When I do that, first look at this. What I'm plotting in red is the correlation induced feature, the Hubbard band. And in blue is the coherent feature, or the doped electrons. And looking into the system, remember, we are looking down into the LTO and compare it with this theoretical prediction. You'll see this incoherent feature grows very rapidly. This is the interface level. Starting from very low intensity, very rapidly the intensity increases, just the way we see here how the intensity increases of the correlation induced feature. Here, the intensity of the coherent peak increases and then decreases, exactly what you see here. It's very low, it is increasing, And then it is decreasing because what you need to look at is only the occupied part that the photo emission can see. You can see here the occupied part is so high, and then it becomes less and less and less. And by this time, there is nothing left. We seem to see an exact replication of this theoretical prediction in our data. We can also do more carefully how the ratio changes, compare with the theoretical data. Theory had a symmetrization. So you need to look at the total 3D electron, how it changes. This is the line. And in our calculation experiment, we see the change like this. Very similar to that. And the measure of the correlation, how the intensity of the correlated peak changes, is shown over here. And that you can see is replicated by this experimental data, showing a very close agreement with the theoretical prediction. Theory, of course, deals with idealized thing. In this case, there are oxygen vacancies that play a role, making certain deviation, etc., that we are not taken care of within the theoretical results. So with this, let me end my talk, leaving the last 5 minutes for the discussion. Thanking you very much for your attention. Thank you.
Thank you, sir. Am I audible, sir?
Yes, you are.
Thank you for this talk. So now I'd like to give the time to the audience. And if you have any questions, please ask, sir. First, I would like to give the chance to the online participant who are in the online platform to ask their questions. Then we'll move for the offline.
These are the difficulties of the online activity because you are not interacting with your audience and they're shy to ask you questions or so it's okay. If they don't have questions, that's absolutely fine because we are running 5 minutes late, so we can save some time and that is all right. I mean, don't worry.
Somebody's initiated for online participation. Participator initiated to ask in the question. Anybody? Sir, I have just the basic questions, if nobody's have the questions. Regarding some Mott insulator, so you have just given the example of the two system. So if we take the one system as a Mott insulation, so now is a latest material we are having to show the Mott insulation properties. So can you give some idea of some latest material which having the Mott insulation properties?
Yeah, many. Nickel oxide is the most classic example that is often discussed because that's how the main discussion had started many decades ago. Why is nickel oxide insulating? Because nickel oxide has 8 d electrons. Since d level can take 10 electrons, it should be metallic because it's partially occupied. Whenever you have a partially occupied band showing insulating behavior, you should think in terms of, unless there is some structural distortion, you should think in terms of Mott insulator because the way you can derive, so basically it says, why does something become metallic? You have suppose d8 electrons and suppose electrons don't interact with each other. If an electron hops from d8 to the next one, it becomes d9 and this becomes d7. And that's the same energy if electrons are not interacting with each other. So it should be able to hop without any energy, which means it's metallic. The electron can hop around and go everywhere. But if electrons interact with each other and large interaction energy. Then when the electron hops from here to there, the difference between the two D8 configuration and D7 here, D9 here, is actually the Coulomb interaction energy. So the energy associated with hopping to the other side is Coulomb interaction energy higher than when it doesn't hop. So if this energy is very large, it doesn't allow the electron to hop, though there are states available. So it's partially filled, so it can hop in terms of count of states, but if it hops, Coulomb energy is required, which makes it unfavorable to hop. And so this electron gets localized, and those are the ones that are called Mott insulated. So all nickel oxide, iron oxide, all these things are lanthanum titanate in bulk form are all Mott insulators.
Okay, sir. So in the DFT, because when we did a DFT, so we'll have some band structure on this one. But that band structure, whatever the theoretically band structure, what we will not get the math informations. So any other way for getting the information for Mott insulation from the DFT?
So you have to go beyond DFT. Very often, of course, you can get insulating state using DFT also when you include magnetism, for example, because magnetism, particularly most of these Mott insulators are also antiferromagnet, and antiferromagnetism corresponds to a doubling of the unit cell, which is the concept that Slater had introduced. And so you can open up gaps and by some band structure consideration, but that's not the correct description. There are many electronic structure calculations that go beyond the density functional theory, which can take into account this Coulomb interaction in a proper way. For example, one example being DMFT, dynamic and mean field theory. I showed some result of that. I didn't mention about it. In the last part, for example, Zilke, Biermann, and Ambrose, they did that for us. So using that, you can describe the electronic structure more reliably.
Okay, sir. Thank you, sir.
Thank you.
Thank you very much, sir.
Hopefully, I'll see all of you in person next time.
Yeah, definitely, sir. I'll call you, sir. Some event after this pandemic is over, sir. We are very much eagerly waiting for your physical talk, sir. Thank you,
All
sir.
the best.
Thank you very much.
Thank you.
Yes.
Thank you.
Yes.
Bye. Bye.
So, so our session, next session, we have a very eminent researcher from University of South Africa, Professor Srinivasu, sir. And sir already came physically in the last conference. So I would like to thank you, sir, for giving the time for talk this conference, even though he is very much busy with his work. And I just want to brief about the sir biography. And sir did the PhD from IISc Bangalore, and he did the PhD on non-resonant microwave and RF absorption in high TC cuprate semiconductors. He then worked as a postdoc and research associate at prestigious institutions like TFIR, Mumbai, and University of Maryland, College Park, USA, Texas Center for Superconductivity Research, Houston, and as a Japanese Society for Promotion of Science, JSPS Fellow in Japan, moved to CSR South Africa in 2008 as a senior researcher, and then he's a full professor at University of South Africa. He published over more than 70 publications. So, I just want to give the time to sir. So please, sir, you please share your slides.
I go to share and then I say share my meeting window. What should I do?
You please share your screen.
Oh,
Then in the screen, please open the PPT.
share.
Share screen. Screen 1, I think. Yeah. Then you open the PPT. Yes, sir. So you now, it is showing here.
It is showing.
Yeah, it is showing, but in the small window, you please.
I made it.
Yeah.
Okay.
It
Good
is
morning,
visible,
everybody.
Good morning.
I thank the organizers and particularly Professor Jyoti Prasad for inviting me for this conference. And I also apologize that I could not come physically because of the Omicron and flights got cancelled. I actually booked my flight, but later it was cancelled. So I miss you all physically. Also, I apologize that my CV was very old CV, and I guess my photograph also is very old. Therefore, I maybe appearing very young there in the published brief. Anyway, and I also thank the organizers for inviting me for the second time, and also I'll say hello to the young students there and all the distinguished guests and my gurus. Actually, Sir D.D. Sharma is a special namaskar to Sir D.D. Sharma. He is like our guru because we all work there as a, even though we are students of a particular professor, we are free to discuss or interact with any professor there. So it's in ISC Bangalore, all professors are like in a kind of single macroscopic state. That means there's no, it's a IISc is like one quantum state actually. Even though there are different neural nodes, each professor is a great inspiration there. They all do highly fundamental work. So Sir D. Sharma, T.V. Ramakrishnan, Professor S.V. Bhatt, and Kumar, all these people are like, they do everything with love. They even take care personally, even in love affairs. So that, okay, so let me go to my talk. Today I'll be talking about low field micro absorption in nano, micro and bulk forms of magnetic materials, and particularly associated with novel magnetism appearing in these materials. This is my university building. This is the main campus, but actual science is done in another campus. One beauty of this building, because NIT Nagaland is engineering institute, I cannot escape mentioning that 60% of this huge building is a cantilever structure. So that's the beauty of this building. Okay, this is another view of our university. It lies on it is on a hill. It's a landmark structure in Pretoria. Okay, so before I go to this low field microwave absorption magnetic materials, I must first about the actual this kind of phenomenon was first discovered in cuprate superconductors by Professor Bhatt in Bangalore. So the discovery actually originates from Bangalore. Cuprates. This is the time when cuprates were discovered in late 80s, and I just joined the institute, and it was very hot kind of situation. So Bhatt discovered this remarkable phenomenon in one of the cuprates. To tell what it is, I put a figure here. So this is absorption versus magnetic field. You can see the field is swept from minus 50 to plus 250 Gauss. So it's very, very small field. And you can see that there's a huge signal here centered around zero field. Because this is centered around zero field, it is not like a regular resonance signal. This is actually the y-axis is derivative of microwave absorption. So the absorption is around 9 gigahertz or something. So that's why it is called non-resonant absorption. So if you change the frequency slightly, the position of this signal does not change. Unlike the ESR signal, where if any small change in frequency will shift the signal position with respect to the field. So this is totally different. This is the first observation of this kind of thing in cuprate superconductors. And I'm lucky to be involved in this work as a first student there. Then after many years, before that, I want to tell you how we measure actually. Why that thing? Yeah, the measurement system is a very simple one. Like what we need is a microwave source, and then there will be a waveguide, and it goes to the microwave energy is transferred to the cavity, and the cavity stores the microwave energy. And you put the sample in the microwave cavity at a position where you like. So what do you mean by that? In a cavity, there are different, each cavity have microwave modes. So therefore, it enables you to put the sample at either a position where microwave magnetic field is maximum, or a position where microwave electric field is maximum. You can choose the position. Then to measure the absorption change versus magnetic field, you have an electromagnet here. You can control that precisely, and you can actually measure the field by a Hall probe or NMR probe. You can measure very accurately. Then also, to improve the signal to noise ratio, what we do is we use what is called phase sensitive detection system, where there will be a local oscillator in, let's say, in audio frequency range, and that signal is fed to an amplifier.
Professor Srinivasu,
Yes.
sir, I'll interrupt you for a moment. Can you kindly enlarge the screen for us?
This is the, I enlarged it. I don't know how.
Down the screen,
Oh, okay.
there are three options.
Yeah, let me do that. What should I do is
Full
Is it
screen mode, please. Please
There's
go to
full
full
screen.
screen.
yeah.
I think yes.
Okay.
No, down the screen, so you come down. If you can, take the cursor. Yes, behind that, to the right. It's right. That yeah. It's fine. I think it's happening.
Sorry for
Yeah,
this.
now it's fine, sir.
Yeah.
It's okay, sir. It's okay. Yeah, happy to help.
Okay.
Yeah, thank you.
So we feed the audio signal to an amplifier, and then to two modulation coils here. So it generates an audio AC signal, which writes on this DC signal. So the DC field is now modulated by audio AC field. Therefore, what you get is a derivative absorption signal, and that signal is now fed to basically a rectifier, and then it is compared with the phase of audio signal. So therefore, you can set the phase in the instrument. Therefore, the advantage is only compared phase signal will be output, which means that you cut off all the noise basically. Okay, so you get very high signal to noise ratio. So we now take you to what is called low field microwave absorption in various magnetic materials. What is happening? So first observation is in those times when soft metallic manganetes were discovered, which are which are closal magnetoresistance materials. We studied this material for microwave absorption, and we found that there's a huge closal magnetoimpedance in this material. Hence, the microwave loss in this material strongly depends on the magnetic field, and that magnetic field is very, very small. So, if you change little bit of magnetic field of let's say 100 Gauss or something, 100 oersteds, the absorption changes by at least 80 to 80%, which means it's colossal. So this is our first report. Then after that, many reports came in various materials, in various forms. For example, in cobalt-based amorphous ribbons, and then magnetic microwires, and then magnetic thin films, and so on and so forth. And including, interestingly, in conducting polymers as well. So to understand this, I'm just bringing the old result because it enables us to understand what is happening. So what we measure here is, we can say figure of merit, that means absorption in zero field minus absorption with magnetic field, normalized to absorption with magnetic field. Then you can see that these triangles are the albium manganate, polycrystalline manganate was powdered to micron size particles. So this is micron size manganate particles. And then these are the nickel and iron particles, okay? So the measurement was done around 9.9 gigahertz, and temperature is room temperature. You can see that within very few hundreds of oersteds, the figure of merit reaches 80%. That means 80% of absorption was changed actually. In this case, actually, the absorption is changed actually. So the absorption is maximum at zero field, and as you put the field 100 or 200 Gauss, this will be changing a lot. How do we know whether the absorption is minimum or maximum? We actually record the derivative signal, and also parallelly actual resonance signal. And you know very well that resonance signal, any resonance signal has maximum loss at resonance field, and off field it decreases. So by comparing the phase of these signals, we can actually identify experimentally whether it is a microwave absorption maximum at zero field or minimum at zero field. If it is a minimum at zero field and it increases with field, it is known to be normal microwave absorption of LFMA, low field microwave absorption. And if the absorption has maximum at zero field, and if it decreases its applied field, it is known as anomalous absorption. And okay, here we sample in actually in the cavity where the microwave magnetic field is maximum. That's how even resonance, electron spin resonance measurements are done, because we want to couple the microwave field to system in the sample. Okay. So here in this graph, I show that different manganites. This solid circle is LBMO, and solid squares are LSMO. And then this is a triangle is a piece of single crystal. We observe that polycrystalline powder samples have the highest figure of merit, or low field tunability of the microwave absorption. Now, what we did is, in order to show that it is whether to identify whether it is spin only phenomena or something else, we moved the sample from inside the cavity very carefully from the position where microwave magnetic field is maximum to a position where microwave electric field is maximum. And when we see that, when we do that, where's my cursor? Yeah, when we do that, we see that this empty squares is this data. Is the data coming from when the sample is in the cavity in a position where microwave electric field is maximum. Microelectric field is maximum. That means there's no field dependence of absorption, whatever. Which means that this field dependence which we are seeing, this 80% colossal impedance we are seeing is a spin-only phenomenon. This is the key result what we have seen experimentally. Then there's no, I mean, we don't know the origin of this field dependent or field tunable loss. So many groups started working on this, and what they found is that, for example, in cobalt-based amorphous ribbons, one interpretation is that we measure the magnetization loop, and then we also measure, let's say, magnetoresistance, and then we measure this low field microwave absorption in derivative form. This is a derivative. Now, what we found is a peak, derivative peak, which means derivative peak means it is the maximum of the slope of field dependent microwave absorption, matches well with peak in magnetic resistance and also the anisotropy field of the magnetization loop. So people think that this may be due to, when you change the loop field in an unsaturated state, domain structure, everything is changing and spins are rotating and so on. So that can cause the actual microwave absorption loss dependence on the low field. So that is well corroborated with this matching of derivative with all these characteristic positions of these three independent measurements. However, you notice the interesting thing here that there is a hysteresis in the magnetization loop, and you don't see any hysteresis here. So then the question is, what is really happening here? So this is another data from magnetic FEB and what happened? 1 second, sorry. Yeah, this magnetic film. What is interesting is again this group shows that anisotropy field matches very well with the field micro absorption derivative signal peak, and they say that the interpretation is that in this position actually spins are rotating, and it is that rotation is maximum. Now, question is if spin rotation is maximum, why it should reflect in low field microwave absorption? Why it is correlating? The answer is not there here, but intuitively we can guess that microwave currents are scattered to spin rotation, and if that is so, then the maximum happens here. So the maximum change in microwave absorption as a function of magnetic field, which is represented by this peak, happens here. Okay. Now I show another result. Most of the results shows that the derivative peak of LFMA and the magnetization anisotropy fields matches 1-to-1. Okay, this is the scenario at the moment. And we studied zinc oxide, zinc oxide, manganese iron, protobutan, manganese nickel, zinc oxide. I'm now talking about bulk materials, okay? Because unless we see this, we don't see the beauty as we enter the particles. Here again, in this case, we see a beautiful low field signal, and then this regular ESR signal. Okay. Now, if you see that this regular ESR signal phase and the low field signal phase are opposite, which means that the absorption has minimum at zero field and it increases with field. Number one. So this is the same case with nickel manganese codope system as well. We have seen a huge signal, and then what we did is we tried to understand the hysteresis behavior. Again, it looks there like as though the derivative peak matches with the anisotropy field. And when we go to low temperature, what happens is, see the scale here, this is the magnetization loop. Scale is 20 kilogauss. I mean, yeah, so plus 20 kilogauss. So there's a huge hysteresis loop. And then when I measure the low field microwave absorption, the hysteresis collapses. So this is not, there's no one-to-one relation here, as has been previously reported. Because nobody actually studied the hysteresis very carefully. I mean, when you do room temperature measurements, everything looks fine and everything looks well correlated. But unfortunately, when you go to low temperature, the real things come out. So this thing is very surprising. Then we analyzed and we found that so room temperature one-to-one correlation between LFMA peaks and anisotropy fields of MH curves collapses at low temperature. And one of the reasons why the loss is coming so strongly could be due to spin polarization in this material, because if the domain spins are rotating and you have spin polarized microwave current, then that interaction can lead to higher scattering. So it is one of the reasons why we see that LFMA signal in this material. Why I am telling this is that not every magnetic material will show this LFMA signal. Only few materials are showing. And if you see that zinc oxide, when we dope with iron and nickel, etc., have intrinsic spin polarization, which can induce spin polarizability around 45% or so. So the loss comes from resistive component. Okay, so the loss reflects in the spin depth and surface resistance to the resistive component, and that resistive component has many components. Simple ohmic component and also the Hall component. Okay, so one of the components, namely the anomalous Hall resistance component, depends directly on magnetization, whereas the normal Hall component does not have that one-to-one relation. So you can have the anomalous Hall component playing a role. Therefore, it looks as though the magnetization and LFMA is matching. But as you change the temperature and when you cross over from anomalous Hall component contribution to the normal Hall component, the hysteresis correlation collapses. When we in the manganites, what we observed is one of the interpretations what we give through experimental evidence is that there's a huge disorder in the system, and that disorder is reflected in line weights of ESR spectra. So we believe that maybe the disorder is playing a role. Now we wanted to look into a very heavily disordered system. So we took this system, which is a multiferrite double perovskite and which is highly disordered. Because there are clusters with highly rich iron and highly rich manganese sites. There's a huge inhomogeneity, and this inhomogeneity is very interesting for us for our low field microwave absorption investigation. As we thought, we see this appearance of low field signal, okay, and then this is the regular ESR signal and is opposite in phase, so the absorption is minimum and increasing with field. Then what we see is that if you do the low field hysteresis measurement, we see that around 45 Kelvin, this hysteresis collapses, and then even the line shape changes tremendously. Okay, this is the observation. Now, if we measure the hysteresis magnetization, if we measure the magnetic hysteresis loop, hysteresis keeps on increasing as you lower the temperature. As you can see, from 300 to 70 Kelvin, 70 Kelvin loop is huge. But whereas here, if you take 70 Kelvin of the LFMS signal and the magnetization loop, it is completely different. So this has nothing to do with magnetization loop. Then if you measure the line width of the TSR signal, we see that huge line width increase as around this temperature, below 50K, indicating that there is a huge disorder coming, inhomogeneity coming, because that is because of the two pin subsystems of iron rich and manganese rich clusters. So our measurement shows that subsystems are working, and at different regions we see different clusters contribution dominantly. And this 45 Kelvin where the hysteresis collapses also matches with the second derivative of the magnetic susceptibility measured on the same system for a zero field susceptibility. So this is about, this peak is about the temperature. So this peak also corresponds to the region where the subsystems, the competition between the subsystems is at its maximum. That means it's in a kind of frustrated region. Now the question why the low field microwave absorption and magnetization responses depending on the two subsystems, but then they are totally different, is still a theoretical debate. We are still working on that. Now we go to the low field microwave absorption and multiferrite farad nanoparticles. They are obtained by sol gel method, and these are synthesized at National Nano Center at Madras University, Professor Balakumar's laboratory. And the typical size is about 50 nanometers. And you see that huge low field signal here. And this is the regular ESR signal. Again, phase is opposite, and so the minimum at zero field and increases with field, the microwave absorption. Now we measure detailed hysteresis loops in this sample, and we can see that low field absorption hysteresis goes on decreasing field, and around this temperature it is almost collapsed. And what we did is we actually measured, because this bismuth ferrite is supposed to be having this jump DM interaction where the spin canting comes into picture in the antiferromagnetic spins, and then because of the spin canting, there can be weak ferromagnetism coming through this DM interaction. Now this DM interaction can be written like this with the two spins and coefficient D. This is coefficient D measured as shift G factor normalized to free electron G factor. Describes it's a measure of degree of spin canting. So we measured that. We see that in BFO, we see a broad peak around this 75 or so. Okay, so if you go back to this thing, we can see that hysteresis starts developing from this around this below 80K. Okay, and it goes on increasing. See, so this whole regime from 80K to 10K, where we see the low field microwave absorption hysteresis, matches well with this broad peak, basically. So that's where the spin canting is maximum compared to at high temperatures. So when you change the field slightly, the canted spins should be responding to that field, and you are actually changing the orientation, basically. So then when you sweep forward and backward, if there are no hindering or centers, then everything should match. There should not be any hysteresis. But probably there are defects, either surface defects or intrinsic defects in these nanoparticles. So in this heavily canted system, the defects can pin down the rotation, and therefore we may be seeing the hysteresis. So this is so powerful. ESR is very, this low field signal measurement is very powerful. You can actually target this area. Okay. Again, the bismuth strontium doped bismuth ferrite. Again, we see this kind of strong hysteresis dependence, and it collapses between 150 and 200K. So there's a critical temperature below which we see the hysteresis. So if you see the measurement of on this system, the spin canting parameter, you will see that there's a broad peak from about this temperature to between 250 and 200 it rises, and then about 200 the canting is really good, and then of course it falls at very low temperatures. So this again matches very well. You see, hysteresis begins around 200 and then it increases and then increases and then again it comes down. There is a one-to-one correspondence between the spin canting parameter and low field microwave absorption. This is the key result which we obtained in this bismuth ferrite nanoparticles. Similarly, the gadolinium and bismuth ferrite. So sum up this scenario, beam interaction can enable an unprecedented control of AFM order by small magnetic field. Now this is actually key theoretical result. Small magnetic fields can actually influence the scanted system. Okay, so this I think we are seeing experimentally in our system. So low field is able to modulate the spin order, giving rise to possible scattering of microwave currents. However, the spin order modulation is hindered by defects leading to hysteresis in low field microwave absorption. The fact that hysteresis occurs in the same window of temperature where spin canting parameter or DM interaction vector has broad peak clearly tells this. Now we go to conducting polymers. It was a very old result by Kyrolin. He studied almost all the conducting polymers, and he observed that that almost all of them have same signature, namely he measured the low field microabsorption as well as the ESR signal in the system. So the ESR signal and the low field absorption signal are out of phase, which means that the low field absorption signal has a minimum at zero field and increases with the field. The explanation given to this is to spin selective hopping process between polar ions and bipolar ions that occurs in these polymers. This is the reason. So you can see he has studied most of the polymers, okay, all are conducting polymers. But to just understand this, we have selected Pani, which is also a conducting polymer, and we decorated that with iron nanoparticles. I did not do this. It's a collaboration. This whole synthesis is done in PSR in South Africa, Pretoria, with my collaborators, and then we got the samples from them. These are all highly well characterized samples. So we can see the iron nanoparticles on these fibers, Pani fibers. The typical size of nanoparticles is about 14 nanometers, and the fiber diameter is about 70 to 90 nanometers. That's the average diameter because you have iron nanoparticles decorating on the fibers. Okay. So now we observe the following thing. If you see the blue is the pure Pani without any iron nanoparticles, and therefore we see that there's no low field microwave absorption in this thing. So this is the first connecting polymer which doesn't have low field microwave absorption, as compared to the earlier slide where I showed that Kyrolin has shown that almost all the connecting polymers showed the low field microwave absorption. Now, once we put iron nanoparticles on the fibers, Pani fibers, we see a huge low field signal here, and then also pure iron nanoparticles also measured. But with Pani, if you take the same sample volume factor, basically, then we see that the Pani fibers decorated with iron nanoparticles has bigger signal, stronger signal than compared to the simple nanoparticles. This result is different because the qualitative signature, namely, here the microwave absorption is maximum at zero field and it decreases with the field. Then we studied the hysteresis, both magnetization hysteresis and then magnetoresistance, as well as the low field microwave absorption signals, which is plotted here. You can see these are the magnetization groups as a function of temperature. This is magneto-resistance as a function of temperature, again in the same regime. And then these are the low field microwave absorption derivative signals with different temperatures, same temperature, measured at same temperatures and with hysteresis loops. As you can see that the hysteresis in magnetization loop does not correspond to the hardly any hysteresis here, you see, whereas there's a huge hysteresis here. So when we draw back the attention to the earlier reports of several groups, that there is a one-to-one correspondence between anisotropy field in MH loop and LFMA derivative peaks. The interpretations by these groups are that the spin rotation is maximized at anisotropy fields, and therefore this correspondence happens. But if you see the Pani iron system, such one-to-one correlation between MH loop and derivative peaks of LFMA is not perceived. In fact, the LFMA signal has comparatively or negligibly less hysteresis compared to the MH loop hysteresis. So this fact shows that this LFMA neither correlates well with anisotropic fields nor coercive fields, and rules out the origin of LFMA from low field spin magnetization process, as described earlier. And even that mechanism of pole-run bipolar because it is where through that mechanism one expects the microwave absorption to be minimum at zero field, and then it should increase with field. But here it is the microwave absorption is maximum at zero field and decreases with field. This is another clear picture here, just to show a clear at tank and room temperature. You see that neither at room temperature nor at low temperature, the magnetization loops hysteresis matches with the low field microwave absorption hysteresis. It is completely different. So, partial conclusion on this penny nanofibers is that these are prepared by this simple reductive deposition of iron nanoparticles on pre-synthesized penny nanofibers matrix. Systematic microwave absorption measurements were performed in order to convey more understanding of LFMA phenomenon in non-degenerate conducting penny, and also the penny iron nanoparticles nanocomposite system. Although LFMA signals in other non-degenerate conducting polymers showed that there is a signal, whereas the penny system does not have any low field microwave absorption signal. Absence of low field microwave absorption in non-degenerate penny might be due to low put state of penny itself. And another thing is LFMA was observed for both bare iron nanoparticles and penny iron composite nanofibers. So a signal observed for penny iron showed that microwave absorption has maximum at zero field and decreases with field, which is exactly opposite behavior compared to one expected for a polar on bipolar on based mechanism in non-degenerate conducting polymers. Actually, one-to-one correlation between this loop, hysteresis loops, doesn't happen here in the case of penny iron system. So the LFMA phenomenon in non-degenerate conducting polymers and the nanocomposites is very fascinating. Most importantly, for applications point of view, one can actually induce this low field tunable microwave absorption in a polymer that doesn't have any low field microwave absorption by decorating with magnetic nanoparticles. This is the nanotechnology part, where you use your nanoscience skills to obtain a material which has new functionality. What is this functionality? Why we are interested in this kind of thing? You know what? There are microwave absorbers from long back, okay? But a microwave absorber which can respond to small magnetic fields, that means using a small magnetic field of 100 Gauss or so, if you can tune the microwave absorption from minimum to maximum or maximum to minimum, that means you have basically a kind of switch. So you can switch the absorber to absorb or make it not absorb. That means you have full control. So where does these things can be used? For example, let's say you are in a plane, you boarded the plane, and then after a few minutes, the air hostess announces that please switch off your devices because they may interfere with the getting signals. So now here there's a polite request and we oblige the request, okay? but a terrorist will not oblige. So the way we can, this kind of tunable microwave absorbers, that means if you, earlier I showed you the bulk materials like manganites and zinc oxide bulk material and also that another material. But if you have a nanomaterial, nanoparticles, which can show that low field tunable microwave absorption functionality, then you can actually mix this in a kind of paintable matrix, and then you can paint the plane, and then you can have a situation where you can actually control the microwave environment, RF signal environment inside the cabin. So then what happens is you don't request people. You just the cabin control will just switch off for RF signals inside the cabin, and it will be signal free. And once it takes off, of course, people want to entertain themselves or communicate with ground, friends and relatives. Then you can switch on the functionality. Okay. So this is the beauty. This can happen only through this nanoparticle, not the bulk. So our ability to show the kind of functionality in bismuth ferrite nanoparticles, it's a multiferrite material, and this low field tunable microwave absorption is a new functionality actually which we established. And similarly, this Pani iron nanoparticles. So basically, you can with our nano science capabilities, you can design a material and import this tunable microabsorption functionality into the material by just manipulating the material with our nanotechnology skills. So this is the beauty of this functionality. So you can generate environments, military areas, and even normal household environment where you may need a place where you don't want any RF signals contaminating your living area, because people are also worried about this huge microwave environment, 5G technology coming up. We don't want, at least in some living areas, we don't want that, let's say. Then our solution is through this low field tunable microwave absorbers that can happen through this nanoparticles which have this new functionality. So I think my time is up. I'll do an overall conclusion. Low field microabsorption is observed both in bulk and nanoparticles, and the nanoparticle thing is a new functionality and new result. This low field microabsorption as a fundamental phenomenon, it can be both normal and anomalous. The hysteresis observed in low field microabsorption can be different from magnetization hysteresis. We established that spin canting and DM interaction plays a key role in low field microabsorption in bismuth ferrite, for example, in bismuth ferrite nanoparticles, where this spin canting is really playing a role. Low field microabsorption is a new functionality for the multiferrite bismuth ferrite nanoparticles. Decorating with suitable magnetic nanoparticles can induce low field microabsorption polymers such as Pani, which doesn't have this functionality. So low field tunability of microabsorption is useful for designing microwave absorbers, and nanoparticles are key because the advantage is then you can make paintable. So you can paint anywhere like you paint, and then you can have that this functionality to control the microwave or RF environment in both household and as well as domestic and select military areas and also aerospace, travel, etc. I think the work is done. It's a teamwork. So I guess in this field has generated a lot of PhDs and good publications. And we have collaborations from Professor Anvi Ma from Chinese Academy of Sciences, Professor Shimayoma from Tokyo University, Professor Balakumar from National Nano Center, Madras University, Arjun Maiti from CSAR, Professor Jiadu from CISRO. We are now trying to do terahertz measurements at CISRO, Australia. Edmundo Giuliani is a specialist in high temperature, high pressure synthesis. So samples are from their laboratory as well. And Professor S. Srinivasan, I think he's in the audience. I don't know. Maybe tomorrow he'll come. He's my best friend, and he's with me a couple of years back. And in fact, we have observed this phenomenon in Hitler alloys as well. I did not include that because I thought that maybe Srinivasan will maybe show some of the results to you at this moment. So I thank you for all for your kind attention, and I would like to hear some questions from audience.
Thank you very much, sir, for very interesting topics for microwave absorption in the low field region. So I'd like to give the time to the audience who are in the online platform. So if any questions and doubt, please ask the question.
Can I ask a question, please?
Yes, sir, please.
Yeah, I have a very naive question. I think way back in 87, Professor M.D. Shastri had studied this possible role of Cu2 plus Cu4 plus pairs in the superconductivity of YBCO. My question is, if you reduce this YBCO to nanoparticle sizes, will you still see the same effects?
So the origin you are talking about cuplate superconductors, okay? So
yes,
cuplate superconductors. The one beauty of cuplate superconductors is a very short coherence length, and therefore coherence length in the order of few angstroms can lead to even small vacancies and defects and converts it into weaklings. Okay. So essentially, this low field micro absorption in superconductors is attributed to weaklings. As you change the field, the Josephson network progressively breaks down. So the weakling becomes normal, and that region contributes to additional micro absorption. So a strong low field absorption signal. That is one thing. And then the other thing is fluxons driven by microwave currents. Okay. So fluxons can nucleate within these weaklings at very low fields. So the HC1 for weakling is less than an Orsted or so. So both ways, because the coherence length is smaller than your nanoparticle, let us say, you should be seeing this even in nanoparticles. And MD Shastri, I know very well. After Professor Bhatt discovered, there are many groups who followed that discovery. The Bangalore discovery has inspired a lot, and BRC also followed.
Thank you.
Any more questions? Yeah. Ma'am, please come here. This side. Okay. Yeah.
So can I? Yeah. Hello, sir. First of all, we would like to thank you for your time and very insightful presentation. I am completely from a different field, but as well as I am very much interested for interdisciplinary research. So I have a question that for there are different sets of nanoparticles, magnetic nanoparticles, and they are showing different kind of hysteresis loops. So just by observing the hysteresis loops, is it possible to comment anything on the nanoparticles activity or its potential healing power, potential activity by even a qualitative.
You are talking about hyperthermia or what?
Yeah, yes.
Okay, so that's a different story. You know, heat the nanoparticle with AC alternating magnetic field. Okay. Well, this is an interesting thing because see now we are seeing novel magnetism in materials with novel magnetism, particularly unlike the traditional magnetic materials where the magnetization is origin is simple. Simple ferromagnetic state or simple paramagnetic state is different. But now, if you have systems where that DM interaction and so on, where spin can have an antiferromagnetic state, but then there's a huge spin canting, and that spin canting induces due to DM interaction weak ferromagnetism. Okay, this is a regime where physics is completely changing. Now the question is, I did not work on hyperthermia, but the very interesting thing would be to check the hyperthermia in this regime actually. I don't know whether you get a very good applied physics result or not, but you will definitely get a very interesting fundamental result if you work in that regime. So if you select a sample where
We are already Porasar's group. They are working on hyperthermia kind of phenomena.
yeah.
So,
So
yeah.
if you are good, if you have a good skill of measurement of hyperthermia, then of course hyperthermia is basically for basically idea is to design a material which will generate effectively more heat with a small AC signal, let us say. That is the motivation. But then I would be, as a physicist, I would be more interested in what happens this heat generating mechanism in a heavily spin canted system. Okay. That's the thing I would be interested. I'm not sure that such a thing will yield you a very good hyperthermia material or not. I don't care. But for me, what is the physics happening there? That's the interesting thing. So in our case, it is not hyperthermia. What we showed is that there's a huge difference of low field microwave absorption hysteresis with magnetization hysteresis loop. They don't match each other, and in fact, they're completely different. And that difference is coming because of the spin canting.
Okay, so these two
Response to
things
the
cannot
microwave
be
currents.
Okay.
Yeah, experimentally, they're not correlating, and then it is because of the microwave current scattering through the canted spin structure, and because that canted spin structure can respond to small fields. That's the key critical results published in Nature paper, which I showed you. It's a beautiful paper. Just read it.
Okay, sir. Thank you, sir. Thank you.
Okay.
Thank you very much, sir. Actually, I think I have other question also, but we are already lagging the time. So,
you can ask me later to email.
Yeah, definitely, sir.
Yeah,
If
my
some
email
time
is here. Any students who are shy or who could not get the chance can correspond with me through email. Email is much better, and then we can discuss in WhatsApp as well.
Okay, sir. Thank you. Thank you very much for your time.
Yeah, I also thank you for giving me this opportunity. Okay, I apologize for sending my old CV and young photograph. I'm very old, you can see.
Okay, sir. Thank you, sir. Hope in the
Thank you.
future we'll see you physically.
Yeah, next time I think COVID is subsiding, and I mean nature is coming back to its normal life. So hopefully next conference I'll be there in Nagaland.
Yes, sir. Hopefully so. Thank you, sir.
Thank you.
So our next session, next talk will be the Professor Jose Manuel Barandiran from Universidad de País Vasco, Spain. So he's a very eminent researcher in the field of magnetism. He will be talking on nanostructure magnet. And just welcome to sir. And before that, just I want to brief about the sir. And Professor Barandiran graduated in physics at the Universidad Complutense of the Madrid, where he also defended his PhD thesis in 1979. From 1988 till 2020, he served as a professor of Applied Physics at University of Vasco Country within the Department of Electricity and Electronics. Currently, he is an emeritus professor at the UPV-EHU. Throughout his early career, he was visited several universities and research centers, as Cambridge University, University of Civil, University of Bath, Technical University of Denmark, University of Utrecht, University of Lewis, University of Leeds, University of Osaka, Massachusetts, MIT, Boise State University, Laboratory Louis Neal Institute, Langevin, etc. His main research lies in the field of magnetism and magnetic material, including the application in magnetic sensor and actuator. Among the materials studied are amorphous and nanocrystalline soft magnetic material, Gian magnetic resistance and magnetic impedance material, rare earth permanent magnetic shape memory alloys, etc., in form of bark, powder, single crystal, thin films, and melt spun ribbons. He have been frequent user of advanced experimental techniques as Mosby spectroscopy, Newton and Mean scattering, and X-ray absorption as EX, EFs, Zanks, and magnetic circular dichroism. He has over 500 paper publications and over 9,000 citations, reaching of a H factor of 45. He has supervised 19 PhD theses and registered 7 patents. Since its creation in 2012 to 2018, he has been a scientific director of Basque Center for Material Application Nanostructure, including the BERC, Basque Excellence Research Center, program that dealt Basque government. He has been integral part of several scientific societies as the IEEE Magnetic Society, the Spanish Class of Magnetism, International Scientific Community, SMM and EMSA conference, and has also chaired several international conferences on magnetic material. So I just want to welcome and from the NIT Nagaland community to sir. So thank you, sir, for giving your time. So
Thank you very much.
want to.
Thank you very much, Professor Bora, for your kind invitation and for this nice presentation you did of me. I'm with a small trouble to share the screen because.
Yeah, the previous speaker has to stop sharing, please.
Oh, okay, because I was, yes, I was trying. So
Srinivasan sir, please.
Yeah. No, probably, yes. Let me see. If I'm able to make this
please share your screen.
No, tell me to change the preference of the system, but I'm unable to do it. So open system preferences, but nothing happens. So I don't know, how can I share my screen for this talk?
So please share, bottom is there in the bottom. You please share it and then share the screen.
Share, but there's a pop-up that allow WebEx to share my content. And
yes, sir, yes.
But I cannot open these system preferences here. Maybe something is not working properly, or I don't know. Could probably, I don't see any other. Yes. No, probably.
I think I clicked the unshare. Is it okay from my side?
Yeah, sir. It is okay from your side, sir. It is okay.
Okay. Yes, I hope it's good, but I don't know how to make this. I hope it will work now, maybe. No, it's still asking for this. Open the preferences.
Something. Sir, or we can do one thing. Please send your slide to my mail so that I will share from the presentation.
Okay.
Yes, sir.
It's probably too heavy. I don't know if this will work. Yeah, well, let's try.
30 megabytes. Probably is too much. I try, but I will try to make it something is, yeah, it's too heavy. Probably it will never work this way.
So please send a slide to my mail so that I will share that one on my system.
Yeah, but problem is that it's too heavy. It's 30. So I will try. Yes, give me 1 minute. Sorry, to make
Okay, sir. Okay,
this the file.
Manu,
Yes.
are you using Apple Macintosh?
Yes. Yes.
All right.
That's my problem, probably. Yes.
It should still work. If you check the open preferences, probably you can.
I did, and I tried to accept that WebEx use my Vivacity,
Yes.
but I'm unable. Yes, that didn't work. I don't know why.
Another option is you can press Control Shift and D. D for
Yeah.
Control Shift and D.
Let me try with a compressed version, which now is probably. It's only 14 mega. Now it works because the weight is not so big. No, return it to sender. Wow. Let me see. I'm trying to do it here.
Yes, sir.
But I don't know how to. So I'm allowing the application.
Actually, in the Apple, we need to give the instruction and that we are sharing the content on behalf of WebEx like this, sir. There is a pop-up is coming, I think.
This is
Give the permission.
terrible. I'm trying to share the PowerPoint, but I cannot find PowerPoint here.
Not the entire screen. You please share the entire screen.
Sorry?
Entire screen, not the particular slide, sir. So that entire screen will be visible.
Yeah, but I don't know which is the way to do it. Yeah, I thought it was more easy, but it's not. So.
Sir,
I'm sorry.
it's okay, sir. It's okay, no issue. Sir, kindly click on the share button once again. In a WebEx, kindly click on the share button once again, sir. And there will be multiple options. You go for entire screen. Once you click on the share button on the WebEx, there will be multiple options.
Ask me to open the preferences. I open the preferences.
Yes, sir. You have to give permission for accessing the screen.
But this is not the screen. It's privacy. Allow the following application to.
Yes, you have to allow, sir.
I don't know. I don't know how to do it.
Sir, no problem. In that case, if you find difficulties, kindly send your PPT to our convener mail ID. We will share, or you can use WhatsApp also, and we will share your PPT from here, our side.
But I tried to send it, but it is returning because it's too big for the mail. It's 14 megabytes. I don't know if this is...
It should work. It should send it to a Gmail address, or you send it to my Gmail address.
I was trying to send it to this.
Can you please send it to me? I'm Vasu here.
To
Vasu.
Vasu. Okay.
Yeah.
Sir, can you connect mic and
Vasudeva Gmail. Okay.
Yes.
Presentation. Let me see. Compress is 14.5 megabytes.
That's okay.
Not on delivery.
You would need to, Manu, you need to send it from your Gmail, not the
Not the
ESU.
official one. Okay.
Yeah. The official one will not allow you.
Probably.
Yes. Please send it from your Gmail address.
Okay. Let's try now.
Yeah, it should work.
It's gone, but this time there is no undelivered. Maybe you are getting it.
Yeah, let me check.
Okay.
Yeah, it has come.
Aha. Thank you very much.
Professor Bora, I will forward this mail to you.
Okay, sir. Please, sir. In the Gmail account, sir, do you know the Gmail account? Or if the email is not working?
You please let me...
Probably you can share it directly. No problem with that.
Yeah.
Anyhow.
Can you please tell me... Sorry?
Juti, JYOTI 2807.
JYOTI
2807.
2807 at gmail.com.
Yes, sir.
Yes, it has gone. Yes. Have you received it, Professor Bora?
Yes, it is received here, sir. Just give us 2 minutes. We'll share from here. Thank you, sir.
Fine.
So, well, if you allow me, I just want to emphasize that nanotechnology and nano-sized objects are especially interesting in magnetism because many of the lengths important in magnetism are in the range of the nanometer. A nanometer is a few nanometers is the interaction between the exchange interaction or the exchange correlation length, better, the size of the single domain particles, and so on. I see that in this conference there are quite a few talks about magnetic properties, and that's because of this particularity of the magnetic interaction to be in the order of the nanometer. For let's say going a little bit in advance to the presentation itself, I prepared a short overview of the interaction between magnetic nanoparticles to see how this interaction is fundamental in determining the magnetic properties of any material. In this case, okay, thank you very much. So in this case, if you can switch to the outline, yeah, I will comment on the second. Okay, on the second slide.
Next slide.
Because the presentation has been already done, so no, it's not a problem to.
Sir, please instruct whenever you're sliding the slide.
Yeah, please switch to the
next slide.
Yes, because the presentation has been already done by Professor Borah, so there's no need. Please, can you switch?
Next slide, please.
Next slide,
Make it full screen, Dr. Borah.
If possible, it should be better, yeah. But I think it's okay. Well, so this is the range of coercivity, HC, or the field needed to reverse magnetization as a function of the radius of a particle. For long or quite high radius, there are multi-domain particles. If you arrive decreasing the radius to a critical size, it disappears. You get a single domain particle. So the particle is a kind of a permanent magnet by itself. This is a critical radius for single domain particles, is in red on the low part of the slide, single domain, and depends on the exchange A, the anisotropy K, and the saturation magnetization M. If you decrease the radius of the particle, then the magnetic state of the particle starts being unstable in the temperature excitation, or the energy of the temperature can switch the magnetism, and then you get the superparamagnetic state. Superparamagnetic state is a combination of magnetism and temperature. Then you have to see it, see it as a competition, and there is a blocking temperature below which is magnetic and above which is paramagnetic, but with a super susceptibility. So for the typical range of magnetic material, this is a few nanometers, the superparamagnetic limit, and also the single domain. It could be twice one of the other, something like that. So next slide, please. But if the magnetic particles interact each other, exchange tends to align the magnetic moment in a single direction, and anisotropy tends to direct the magnetization in the easy axis. Then this competition averages anisotropy, and this is the idea of Giselle Herther, who gave an explanation to nanocrystalline materials. So the average of the anisotropy can get a very, very low, let's say, resultant anisotropy if the small nanoparticles are interacting, and then coercivity also is decreased. So we have a strong magnetic behavior for isolated particles, single domain. Each particle is a hard magnet, let's say, or you can soften the magnetic material by averaging the anisotropy in this circle. In fact, it's a sphere in 3 dimensions of the exchange correlation length. And that depends mainly on the anisotropy of each particle. Can you switch to the next slide, please? So the idea is that at high diameters of the particles, the magnetic state is a multi-domain, is easy to magnetize, are soft magnetic materials. If you approach the single domain, you increase the coercivity, and if you decrease even lower, you average anisotropy and you get a very soft magnetic material. Indeed, the intrinsic anisotropy of the material plays a role. So here you can see two curves with this maximum coercivity at about 100 nanometers or 20 nanometers, which depends on the anisotropy. The red one is for permanent magnets, like neodymium iron boron magnets, who can get several Tesla or kilohertz of coercivity. The black one is for nanocrystalline materials, nanoperm or fine met, which can get in the interesting range, which is a low 30 nanometers, for instance, is approximately 1 amp per meter. That makes a difference of practically 1 million in coercivities. And also, I want to emphasize that the composition of the magnetic material is very, very similar in both cases. Only the size of the particles and the coupling of the particles determines the coercivity. For instance, for the softest known material, the composition is iron, niobium, boron, copper. And this has a coercivity of 1 amp per meter. But the hardest permanent magnet known is neodymium, iron, boron. So you change niobium by neodymium, and a little bit of copper for refining the grain in the case of submagnetic, and you can change for 1 amp per meter as coercivity to 1 million amps per meter coercivity. Next slide, please, can show the two extremes of the material. Next slide, please. So the softest one is this nanoperm or fine met, which is only possible by this, let's say, structure, nanostructure and coupling of the particles, which is above the limit, the classic limit for normal materials, or conventional, let's say, not normal. Everything is normal here nowadays. Conventional materials, although the other materials, typical materials, including silicon steel, permalloy, cobalt-based amorphous even, are either harder or lower magnetization. So this is the softest magnetic material, is an nanocrystalline material. Next slide, please. But the hardest on the magnet is also a nanocrystalline material, nanomicro, and this neodymium iron boron. Difference is that in one side is almost pure iron. Here, neodymium iron boron is a tetragonal compound with very high anisotropy, both crystalline and magnetic state. So, in fact, the hardness, the coercivity of an ensemble of magnetic nanoparticles depends indeed on the intrinsic anisotropy of the material, but also on the size of the grains and the coupling of the grains. Can you switch next slide, please? In this sense, we did a very old paper by studying the coupling and uncoupling of grains through, we were interested at that moment in very soft magnetic material, so coupling or not coupling of the small crystal nanoparticles were done through an amorphous matrix, because the nanocrystalline state was obtained by crystallizing an amorphous. And this is a calculation. So uncoupled grains have different coercivities, but once you couple, you decrease the coercivity by a factor of 10 or more, even being the initial anisotropy K1 low for all the material, which is mainly iron. Next slide, please, explains how this happens. Experimentally, it was observed by this increase of coercivity as temperature change, and this had to relationship with the coupling or uncoupling when the amorphous matrix that is coupling the grains of this very soft material becomes paramagnetic and is not able to couple magnetically the grains, so the exchange cannot cross from one grain to the other. In the upper part, you see the experiment, and what happens when you reach the Curie temperature of the amorphous, and in the low part is a model taking into account the main magnitudes of the particles and the amorphous, and fundamental magnitude here is the Curie temperature of the amorphous, the surrounding material. So this was one of the papers that we did a long time ago, collaborating with Professor Hernando in Madrid, also emeritus now, and with Herther himself, that developed these materials in vacuum smelt in Germany. Next slide, please. So the say interaction between particles adds just the influence of the size to the magnetic properties. This was the conclusion of that paper, how different cases of coupled grains, partially coupled or uncoupled grains, can give very different magnetic properties. In the very soft side are the completely coupled grains. Also, you will need a low anisotropy, both to extend the range of the coupling and to start with a low anisotropy and become a soft material when coupled. In the partially coupled grains, there is some intermediate, like a spring magnet, that make take advantage of the coupling and uncoupling between high magnetization, high coercivity materials in the grains, are completely uncoupled grains give the more hard nanocrystalline magnets. So coercivity is driven by the anisotropy, diameter of the grains, and coupling. In next slide, please. Coupling, for instance, has been recently studied. I thank Professor Thomas Reifert of the new university in Austria, because this nice picture explaining how the intergranular phase, which couples or uncouples the grains, can make coercivity increase by factors of 5. Well, here is for an neodymium iron boron, so neodymium content of the intergranular phase, or similar, is a decrease of the Curie temperature of the intergranular phase can increase highly the coercivity. So with this idea, I want to present some work on permanent magnets. Next slide, please. Nanostructural hard magnets. In fact, I have two works, recent works, done by our group on these hard magnets, neodymium iron boron magnets, and the coercivity enhancement by grain boundary diffusion, so playing with the coupling, and new rare iron 12 magnets that with hot deformation can get also very good magnetic properties. To end, I will come to magnetic nanoparticles for biomedical application, uncoupled particles, but also very interesting, but quite more simple in the behavior, I will say. So thank you. Next slide, please. Nanostructured hard magnets, neodymium iron boron, have quite small grain size. Usually you can improve the grain size and the magnetic properties adding grain refiners, but the coupling between the grain is also important. And usually this coupling and increase of coercivity is done by adding dysprosium, which is a very hard element of the rare earths. But here we were exploring the idea of making low content rare earth magnets by just, let's say, tailoring the coupling and the boundary bond. So the work proceeds by making first a melt spinning to amorphize the alloy, which include a little bit of niobium and copper and low content of neodymium, then anneal to nanocrystallize. Here you see the machine for the amorphization, the called wheel and the amorphous ribbon, which we get, which are a few millimeters wide and a few microns thick. So next slide, please. Then by trying different composition, we saw that really, as it was known, the stoichiometric compound with the right amount of rare earth is the best. But we have a lean, neodymium lean, or let's say low concentration alloy that could be also promising, but has an excess of iron because of reducing the rare earth, you get a precipitation of iron. But this red alloy, which is the first on the list, was selected to make a grain boundary diffusion and trying to improve the coupling condition of the uncoupling, better to say, and see which were the results. So next slide, please. I will explain a little bit how the coercivity can increase by treating in the presence of an eutectic praseodymium copper cobalt alloy. This eutectic has a very low melting point, then at quite moderate temperatures, it becomes liquid and it permeates the grains, concentrating in the grain boundaries. And at the same time, the excess iron, you can see on the right of the picture, is absorbed by the filtration of this new alloy. So let's say the violet curve, see that the excess iron has almost disappeared, and at the same time, coercivity has increased on the left hysteresis loop. You see how coercivity increases. There is an intermediate state where there are a two-phase. The hard phase and the soft phase are coexisting with these constricted loops. But if you can see, we were able at that time, well, it was 4 years ago, not so ancient paper, that one, to increase the coercivity over 2 Tesla in this case. So next slide, please. We try to see how the different elements were distributed into the grains. You have on the left in black and white, you have the electron microscope image, and 3 other images are done by resulting each element by X-ray energy dispersion in the sample, analyzing that iron is depleted, is black in the grain boundaries, while praseodymium and copper also are rich or are increased concentration in this region. To go a little bit more in detail, next slide, please. I can show you some analysis along the grain boundary in two cases, in two grains or even a triple grain conjunction. In both cases, you see that iron, which is taken from the X-ray signal of the sample, is depleted largely in the grain boundary, while praseodymium and neodymium are increased. So the grain boundary is becoming less magnetic and more anisotropic. So the coercivity increases because of the coupling of the grains of the boundary. This increase can get very good properties. Only problem for this diffusion of material in grain boundaries is that the size of the sample cannot be too big. To diffuse along millimeters, it would be impossible. Only some microns are interesting, maybe half a millimeter, 1 millimeter. Thank you. Could you, next slide, please? So the next work we will present here is the exploration of a new composition, mainly rare iron. There is always some need of a stabilizing metal with the iron magnets. This study was included into a very large European project, next slide please, called NOVAMAG, which ran till 2019. And the new phases, well, no, they are not new. They were discovered in the late 80s or 90s of last century, but now there are more possibilities to do technology, metallurgical technology, and these compounds can give probably a challenge to the neodymium iron boron present magnets. The problem is that they need a third element, apart from iron, another metal, to stabilize the 112 phase of high coercivity anisotropy in principle. In this project, we studied in Bilbao a main new compound, samarium, iron, vanadium, scintillant magnets, and this was the PhD of Ana Maria Schoenhobel, which also spent time in the University of Delaware. The NOVAMAG project included 15 different partners, so there was a large interaction between any possible laboratories and companies for developing these magnets. So next slide, please. I will show you here how there was the proceeding. In this case, samarium, iron, and some vanadium were made by mechanical milling, where they got almost amorphized after the milling. You see the X-ray, which is quite, let's say, bumpy with peaks, crystalline peaks. But once you treat or anneal this amorphous compound, you get crystallization. And for instance, after 10 hours milling and recrystallization at 800 degrees C, you get quite a good composition of the magnet. The material is a low grain, but a complete structure. So next slide, please. You can see that with this new powder, once crystallized, and this was done at the University of Delaware because they have this this possibility. They were hot pressed or compacted in a special induction furnace, or hot deformed. Deforming it was interesting to try to get anisotropic magnets, which was not really reached this aim. So please, next slide. I will show you the result of the hot press on the left and hot deform samarium iron vanadium magnets. The hot press still keeps a very low grain size, even around, you say, 13 nanometers, but after deforming at a high temperature, the grain size grows and many properties are lost, except in a few cases. Next slide, please, where you see with samarium iron vanadium, which could be deformed at 800 degrees, and adding a little bit of copper even, we got 1 Tesla coercivity and more or less reasonable magnetization remanence. The problem is that really parallel and perpendicular hysteresis loops are the same. So the magnets are not anisotropic, but quite isotropic. But in fact, they got a very good properties and more technical advance in the treatment and the processing of these materials are needed. Next slide, please, gets the numbers of the different alloys, different treatments, and the best one, as you see, is the one containing a little bit of copper and hot deform at 800 degrees, not to increase the grain. So you have a coercivity of 1 Tesla, 0.96. Magnetization is not so bad. The 3 Tesla magnetization is 70 amps meter per kilograms, and the remanence is 50, but still are far from the performance of the neodymium iron boron. In any case, as you see, these alloys have much less rare earth than the neodymium iron boron. These are 1 rare earth against 12 atoms of iron, and in this case vanadium, although the neodymium iron boron have 2 rare earth atoms against 14 iron atoms. So the decrease is quite important, and new work is being done all around the world now in trying to discover the best way to substitute neodymium iron boron for this new 112 permanent magnets. So next slide, please. In order to see how these processes contribute to the increase of coercivity, the hot deformed magnets, in NovaMag, we use atom probe tomography technique, which is a very, very interesting technique I want to outline briefly. This was done in the Max Planck Institute. We don't have this equipment. So a tip in the left bottom of very thin metal, a few nanometers, is put in a vacuum in a high magnetic electric field gradient, and with a pulse of voltage or laser, you can evaporate atoms from the tip that travel through the electric field and impinge in this circle, which is the two-dimension detector. Depending on when the atoms arrive, you can get a very amplified image of the tip and know which is the composition of the tip at atomic level. This is atom probe tomography. Next slide, please. So the distribution of atoms in the hot press, which were not very good as magnet, and that's because there was an excess iron, these green volumes on there, which were segregated from the alloy, and in the let's say more homogeneous region, the grain boundary, which has been enhanced here by putting in red, which are the samarium atoms, is like in the previous study, is increase in samarium and copper, and the plated in iron. But this coupling was not still good, and the presence of iron, this two-phase magnet, was not good. Next slide, please. See the formed magnet, in which all iron has been absorbed by the grains, and the grain boundary is much more clear now. You see the depletion of iron in a few nanometers, 1, 2 nanometers, and the increase of samarium. Vanadium is also depleted with iron, and copper is increased in the grain boundary. You see in the low part an image of the atom probe of the samarium and copper distribution alone, looking very, very increase in the grain boundary, the coupling then the grains, and getting this high coercivity after that treatments. Okay, so these two studies mark mainly the size and the grain boundary, let's say, dimensions and composition for obtaining hard permanent magnets, which is one of the of the needs of the energy and electric vehicles, let's say aeolic generation, and many technologies nowadays of great importance. Next slide, please. I will now switch to next slide. To magnetic nanoparticles for biomedical application. Next slide. These magnetic nanoparticles in these applications are completely different. Iron oxide magnetic nanoparticles of the size of the superparamagnetic state. So each particle has between, let's say, 5 and 12 nanometers, and are in mainly magnetite in a superparamagnetic state. Different chemical routes can give to these nanoparticles with high low dispersion in size and highly controlled grain size. The thermal decomposition, for instance, is typical of tiny magnetite, but there is another method also, the inverse micelle nanoreactors, in which a coating, which is in this case a surfactant, polyethylene glycol, can coat, make the reaction inside this micelle, and get magnetic particles already coated. In this case, you can get even pure iron, as the coating prevents oxidation of the particles. You see the particles coated on the right low picture. Next slide, please. We've been working with these nanoparticles for several years, probably 10 years or so now. And the interest of these nanoparticles for many applications is the possibility of functionalization of the particles through the attachment of drugs, antibodies, DNA, or even substance that can target different parts of the body or of biological items. So this can give to the use in diagnosis of diseases, and at the same time to therapy. We will see briefly now. So what is the idea is to make a single drug that can make diagnosis and therapy of theranosis, as they call nowadays. Next slide, please. I can show you, for instance, the contrast for magnetic resonance. Then they are superparamagnetic particles are also similar to gadolinium, which is paramagnetic but very close to the Curie temperature. You see here how a tumor is contrasted in magnetic resonance. This was, I don't know, probably a rat or an animal. And also, the direct detection of the magnetic nanoparticle, next slide, please, is very interesting in some cases. For instance, in the breast cancer, the metastasis can attain some lymphatic noduli, and if you inject into the tumor some magnetic nanoparticles that attach to the tumoral cells, you can detect whether they reach or not the lymphatic modulus, and then if the treatment can avoid or not chemotherapy or radiotherapy, because by chirurgical means you can eliminate the full tumor. This is a very nice work that has been developed by Professor Quentin Pankhurst at University College in London, and we were collaborating with him in some studies of these magnetic nanoparticles. Next slide, please. Tells how the therapy, former was diagnosis, can be done using the magnetic nanoparticles. The nice interest of magnetic nanoparticles is that they can go to specific sites carrying drugs, which can be delivered there because of the pH of the different tumor, for instance, or by heat treatments without any contact through high frequency radio frequency heating or hyperthermia, which can either deliver the drug or kill the tumor cells. This application have been very interesting, and our group has been involved in studies mainly of hyperthermia and of different magnetic nanoparticles. Next slide, please. The only use of clinical use nowadays is for magnetic nanoparticles in therapy is done by these particle Mark IVs, which are, let's say, dedicated to either glioblastoma, a brain tumor very difficult to attack by any other method. This was allowed in Europe from 2011, and is being used normally. And in the United States, quite recently, has been also allowed to be used in clinic for prostatic cancer. Not too many other applications are for the moment available, but I think they will increase in the next future. So finally, next, not finally, next slide, please. Yes, there is another kind of magnetic particles or systems which could be interesting in this therapy. These are the nanodisc. A small disc can have a very strange magnetic structure, which is called a vortex, which is a circular magnetization with a small vortex in the center. If these discs are in absence of any field, they are not magnetic. Only the vortex can have a magnetization, because magnetization is close on itself. You see the hysteresis loop on the right of the vortex, and a nice application could be attached to a cell. A small or low frequency AC field can induce movement, and then by mechanical forces, they can destroy some membrane of the cell and destroy the cell. So if instead of iron superparamagnetic particles, you use this disk, you can get the same or similar destruction without any heating by mechanical actuation. This paper, pioneer paper, was published in 2006. And next slide, please. We were working on this nanodisk in the thesis of Maite Oiriena, which a new procedure to get the nanodisk at a very normal level. This is the whole mass colloidal lithography. You see the permalloy disk in the upper part, and in the lower part, the magnetic behavior through a magnetic force microscope. In the center of the three pictures below, you see the vortex either pointing in one direction or the other in the disk. But if you apply field in one direction or the other, the vortex displays and get magnetization and force on them. Next slide, please. This slide sees the interaction with cells. You have a cell which is divided normally in the first picture up left. This is put in contact with the nanodisk, which is the orange circle in the middle at 21 hours of time of the culture. And the cell is surrounded, attached by the nanodisk. So when the time is passing with this mechanical movement, the cell who got the nanodisk is unable to divide, as other cells in the time in the central picture in the lower part shows. A blue arrow indicates another cell dividing, but the cell which has been treated is unable to divide and finally is dead. This treatment is effective. Probably will take several years to make it a clinical adopted therapy, but in any case, these are kind of nanometric. These were 70 nanometers disk, more or less. So next slide, please. I'm coming to the end, and I wanted to offer you a bonus talking a little bit on magnetotactic bacteria. Why? Because next slide, please. The production of nanoparticles has been done by living beings from a very long time. Most of the migrating or animals do use magnetoreception. Magnetoreceptive pigeons, salmons, bees is common and well studied. Even at very low level, bacteria are not only magnetoreceptive but magnetotactic. So they move thanks of the magnetic nanoparticles they produce. As in the lower right picture, magnetotactic bacteria are very efficient producing magnetic nanoparticles and using as a compass. Next slide, please. So I want to show you an animation of how these bacteria use the hair magnetic field to direct the swimming and to attain what is called the oxic anoxic transition zone, OATS. That is the region where they are more comfortable for oxygen concentration. They are quite anoxic, and for food search. Without this magnetic compass, the possibilities of directions of swimming are so many that they could never reach the comfort position. So this has been developed along millions of thousands of millions of years in these bacteria, and they are very, very efficient producing magnetic nanoparticles. Next slide, please. So I can show you this strand of the Magnetospirillum valdensis that has been studied in our group, which are bacteria producing magnetosome or small magnetic particles about 40 nanometers that form a chain in the bacteria to guide the movement. These magnetic nanoparticles are of very high quality. They are produced by biological methods with very well developed and selected genetics in their chromosome, and the crystallinity is excellent. Then, as a narrow size distribution, are quasi-spherical and biocompatible because they are already surrounded by a biological membrane. So next slide, please. After several years working with this bacteria, now a project has been started 2 years ago on the use of magnetotactic bacteria as nanobiorobots, because as any robot, they have a propulsion method with the flagella. They have a control through the magnetosomes in it. They can be carriers of drugs. They have a sensor for oxygen. The sensor this sensor of oxygen gradient help localizing tumor cells that are epoxy. And then you can use this bacteria also as hyperthermia agents via an external field. This project is a project of the Spanish Ministry of Research and Innovation, and is, as you may see, is highly interdisciplinary. Next slide, please. Is showing the three ladies that ruled this project in our group, which is a physicist, leader of the group, now retired, Maria Luisa Fernández Boveda, a microbiologist, Professor Alicia Muela, an engineer, Dr. Ana García Prieto. So with this, I'm almost at the end. Next slide, please. So I must mention all the people in the group of magnetism and magnetic materials, which have been developing different parts of these projects. And thank you for your attention. Sorry, I don't know if pronunciation is good enough. Thank you very much. If there is any question.
Yes, sir. Thank you, sir. Thank you for a very nice presentation. Hope all the participants are getting the different application of the magnetic nanoparticle in that way. What the way sir is explained, definitely we are getting benefited for this. So now I'd like to give the time to our participants to have any, first online participant, if any have doubts, please ask the question.
Yeah, one small question. I'm curious, let's say we do hyperthermia or some treatment by injecting the magnetic nanoparticles, it goes to targeted area, treatment is done. Then after that, will the particles remain there, or how do you get out?
Sorry, what is the question? Because it was the sound was not perfect.
The question is, we inject magnetic nanoparticles and send it to target the tumor area or whatever, and then using hyperthermia or other mechanical breaking into DNA membrane, whatever treatment is done. After that, will these particles still remain in the body, or will you take it out? How do you take it out?
Well, the iron oxide nanoparticles are not. Well, we never did any trial on real or live animals, or because only in vitro studies were done at our group. So only cell cultures and magnetic nanoparticles and hyperthermia was done by an RF working generator working at about 100 to 300 kilohertz. That's the question. So we don't take the particles off afterwards. But iron oxide nanoparticles can be metabolized by my living people. They are not very complex. Probably the permalloy discs are probably much more difficult to get rid of because this is a metallic item. So probably there will be more difficulties with this particle disc, vortex disc. This is more probably a proof of concept, but clinical application is probably far away if there will be any finally. I'm sorry for this. But magnetic nanoparticles of iron oxide are quite simple to dispose of by biological methods. You can degrade them, include into the blood or proteins or. But I'm not a biologist, so I cannot tell you the mechanism of disposing of the iron oxides.
Okay, thank you. Thank you.
And sir, and other than anybody have a question?
Oh yeah, please.
Okay, I think I need to give the time to the. Yes,
I
sir.
just wanted
Please.
to check. You showed those nice micellar structures of nanoparticles. Have you tried to measure them using any small angle neutron scattering or something like that?
Yes, we did even some trials with all kind of magnetic nanoparticles. I only presented these two ways of producing them, but there are others too. And the size and the magnetization have been studied by many methods, including ILL, small angle neutron scattering. I tried to make some experiments by myself with some nanorods produced by Harry Shrinkan in Florida.
Yeah.
But in my case, there was not very successful. So the results were more or less confused because probably the nanorods agglomerate. This is the main problem always with these things is agglomeration. They must be very well dispersed in toluen, or I don't know the kind of dissolvent that must be used. But once they agglomerate, the neutrons are unable to give individual things. So that's it.
Okay, thank you.
Okay, and I think the participant from the audience, so they might have some question.
Very good morning, Professor.
Thank you.
Yes, my question is related to targeted drug delivery. I think you mentioned related to magnetotactic bacteria, that's what you're working with for targeted delivery, right? Or the use of even iron oxide in remotely controlled drug delivery. So we use hyperthermia in that case for remotely controlled drug delivery to release the cargo, right, sir? In order to.
Yes.
And is it important because for that reason the parameter that we use for hyperthermia is SAR, specific absorption rate, and for the nanoparticles the specific absorption rate has to be high such that all the cargo molecules are transported to the site. So for iron oxide nanoparticles, the heating efficiency or the SAR rate that has been found by most of the researcher is quite low compared to other spinel ferrites. But then there are cases related to cytotoxicity as well. So are you trying to, solve that problem and have a efficient drug delivery system by using magnetotactic bacteria, or are there any other options available?
Okay, yeah, I mean, many different changes in composition and in size and form of the, for instance, the core shell structure of particles have been used to improve the SAR, the efficiency for hyperthermia. In the drug delivery, hyperthermia is not so critical because you don't need to kill the cell by hitting the cell, but just to unbond the drug. I don't think we did any drug delivery experiment by ourselves. In the case of the bacteria, this project, let's say, we've been using the magnetic nanoparticles produced by bacteria as hyperthermia media and doing several trials. Once the bacteria are used to produce them, they are killed, they are washed, and the magnetic nanoparticle extracted, but this is a complex system. The bacteria, the full bacteria itself, is being now explored as a way to deliver, let's say, drugs or to make hyperthermia. But this project has been running for a couple of years only, and it's quite early to give any result on that use of the full bacteria as a nanorobot. We, however, think this is probably promising, so that's why we started this project. So hope I did more or less what you want.
No, yes. So, thank you so much. Last question. Okay, all right.
Actually, we are
Sorry,
out of
we are
time
running out of
because
time, so
another
yeah.
session is going to start. Sorry for interrupt.
Okay.
So I think it's, if somebody have a question, they can write the mail.
You can
Okay.
ask either Professor Bora or Professor Siriguri for my email, and we can talk through email afterwards, if you don't mind.
Okay, sir. Okay, sir. And actually, our group is working in that application of magnetic hyperthermia for ferrite-based nanoparticle. And as well as the group is also working on a non-ARR-based permanent magnet. For generally, basically non-ARR permanent magnet, so far we are working on a theoretical study for iron-based or manganese-based alloys. So we succeeded.
Manganese aluminum, for instance, or something like that? Magnets?
Yes, sir. Yes, sir. Manganese aluminum.
Okay.
Okay, sir.
Okay.
So I think I need the help from your side, so I'll communicate you, sir.
Okay,
Because,
so we can communicate by mail or by Skype or whatever you want at any, not at any moment, but because of the
yes, sir.
time difference with India makes more restricted time to speak.
Right.
Okay, you're welcome.
Okay, sir. Thank you very much, sir, for joining and giving the time to us. Thank you.
Thank you to you. Bye-bye.
Yeah. So I want to request to Dr. P.D. Babu and Sirugiri sir to join the particular session. Babu sir?
Professor Bora, is there any small break?
Sir, actually, we can do one thing. Just start the session, I think, after that. I think you are sharing the session, sir, Sirugiri sir? I think...
No, I'm not sharing any session. I have a talk actually. So I thought if you can give me a few minutes time to...
Okay, no problem. Oh, no problem, sir. And Babu sir, please join that session.
Okay.
Babu sir is...
Okay, yeah,
yes, sir. The another session, sir. I think meeting link is different.
Session, right?
Session number 1, sir. Session 1. No, PD Babu sir, session 1. Yeah.
Professor Bora, maybe
yes, sir.
if it's too difficult for you to take a break, then maybe you can shift my talk to number 2 or number 3 in this series.
Sir, okay, sir, no problem. Sir, Manoranjan Kaur, sir, I will request the Manoranjan Kaur, sir, to give the talk early. Yes, sir. Okay.
Yeah. Maybe if you can give me, I can give after Manoranjan, I can give my talk.
Okay, sir, no problem, sir, no problem. I'll
I
manage
need
it.
just a small break, that's all.
Okay, no problem, sir. I will call Manoranjan.
Okay, thank you so much. Thank you.
Thank you, sir. Thank you all the participants for joining this session. So I just want to conclude this session.
Thank you very
Thank you,
much.
sir. Yeah, welcome.